Mic test, mic test. Okay, let's wait for everyone to set up the translation first. Okay, all good, all good. Okay, so yeah, good morning, everyone, or how should I say it in Cambodia? Arun, Shwaste. I'm pretty sure I pronounced that very incorrectly, but yeah, it's happy to see you all again today, and thank you for all the feedback that we had from yesterday. So now that we have a translator, and I hope the space is also more spacious for everyone. And we also did some adjustments to our content to adjust with the participant spacing. And before I start, I'd like to also just recap some of the things that we promised yesterday. So first, one is the Google Earth Engine setup. So apologies for the hiccups in the setup yesterday. And in line with that, we will after this workshop, we will send setup instructions, a video of how to create a Google Earth Engine account for those who haven't set it up already. And the second thing is the raster analysis notebook. We didn't actually get to um, take take some time on that, but we will also clean up that notebook and send it to you guys. And lastly, the third thing is remember that we did have that GeoPandas Google Colab exercise, and there was at the end, there was a confusion on the symmetric difference calculation. There were two percentage scores that were supposed to match, but they didn't match. So we will be following up on the explanation for that. All right. So with that out of the way, I'd like to open up today's session. So yesterday was more focused on geospatial analysis and GIS methods as well as open data. But for today, we'll be focusing more on machine learning. So yeah, so first to introduce myself again. So hi, I am Joshua Cortez. I am a machine learning consultant from a company called Thinking Machines that's based in the Philippines, but we've also grown in the region. We have an office in Thailand and also in Singapore. So as for myself, I am part of the geospatial machine learning team, and I've had projects in social development and sustainability. But even before joining Thinking Machines, I've already been a data science consultant, also in the Philippines, and I've been working with other applications such as customer analytics for banks. By the way, is my voice okay? Can everyone hear me? Okay. So yeah, today we hope to introduce GeoML. Although we did touch upon that already, some parts of it yesterday, especially when we talked about Rice estimation, but now we'll be focused more on the fundamentals as well as another use case so that people would reinforce their learnings from yesterday. And yeah, so this is what we'll be talking about today. So first is classical machine learning. And the second one is another type of machine learning, but a bit more specialized, which is called computer vision. So in the morning, we'll be talking more about classical ML, and we'll be talking about a specific use case. And then in the afternoon, we'll be talking about computer vision and then its own use cases, especially when it comes to land cover and land use classification. Right. So the objectives more specific to today are to understand what machine learning is in the first place. And you might it's okay if you're not a full machine learning expert at the end of the day. What matters more is gaining an appreciation of what machine learning can and can't do, and also have a sense of how the work in machine learning, what kind of work goes when you do machine learning, as well as what kinds of use cases can you expect to get out of it. And apart from machine learning, also the applications of computer vision with respect to geospatial applications. All right, so first, I'd like to talk about classical machine learning. But before that, what is machine learning in the first place? So there's the many different applications of machine learning. You might have read about this tool online recently called Chat GPT. So that's a chatbot that you could literally ask it anything, and it will provide a reasonable response that sounds like it could have been from a human. But more generally, machine learning is all about making predictions from data. So in that case with Chat GPT, if you're familiar, then it was making a prediction of what a human could have said in response to a question by someone that's writing it. But also, it could also apply to other applications, such as when you're forecasting sales or yield, making a prediction about the future using the data that you have currently. It doesn't always have to be about the future. It could also be about different areas. So given data for this area, but I don't have data for this other area, how can I make a prediction on areas where I don't have ground truth information, like rice yield yesterday. So yeah, good thing about machine learning is that it has the ability to find patterns that may be difficult for humans to see. And the way it does that is through a combination of statistics and computer science, where you collect. So us humans, people will collect data, and then when you feed it to a machine, you train a machine to learn the patterns from it in such a way that when you give it a new data set, it knows what kind of prediction it should give. Right, and then some of you may, when you're reading articles about AI and ML, AI meaning artificial intelligence and ML machine learning, those two might have been used interchangeably. And sometimes it can be confusing. What do you mean by artificial intelligence? And how is it different from machine learning? So this is one of the ways to distinguish it. And the thing is, artificial intelligence is actually a broad area of study that um, applies to both artificial narrow intelligence and artificial general intelligence. And what you see in the movies, when you have a robot that can act sentient, that usually pertains to AGI, or artificial general intelligence, where a machine can do anything that a human can do. It could speak, it could walk and talk everything. But actually, we're not there yet. It's still an active area of research. And when we talk about AI, it's actually more about artificial narrow intelligence. So, and you're already seeing this today. When, for example, some of you might have smart speakers, Alexa, or Hey Google, those products from those tech companies. And also, for example, in the United States, they have self-driving cars. And actually, even more relatable than that, even just web search. When you Google something, it's part of what is recommended to you is powered by artificial narrow intelligence or machine learning. But there are also applications in farming and factories, apart from just websites. So yeah, there's a lot of progress in machine learning in the past 10 or so years. And the gist of it is, how does it work? Is basically computers learn how to do things by training on data. So data is what powers the task, but how these machines can do what they can do. Okay, so this is one way to think about machine learning. So you typically give input data to a trained model to generate a result or prediction. So think of it this: it may be among all that complexity, this is really what it is. So there's a model, and you give it input data, and it will generate a result. And here are some examples of certain applications of what the input is and what the output is. So, for example, you have an application of house price prediction. So maybe you are a real estate company, and you want to know what is a proper pricing for a certain type of house. If you're gonna try to sell it. So maybe what you could do is get a historical data of houses, and you have certain information about each house. You know, how big is the house, how many bedrooms are in the house, etc. And then given all of that information, what is the price, for example, in dollars. So given historical data of how house prices have been, given their characteristics, then we could, given a new data set, a new house where we don't know the price, you can give it to a trade model, and it will generate to you what is the likely price of this house. And another example is in spam filtering. So when you use your Gmail accounts, sometimes some of your emails get sent to spam. And the way that Google does it is there's actually a machine learning model that is running in the background where it knows how to classify if the email is spam or not, given the contents of that email. So, for example, if there's certain kind of keywords that make that email trustworthy, and there's a model that knows that those keywords are untrustworthy. So when it generates a result, it will be, is it spam or not spam? It's just two options. And then the input for that is the text, for example, of that email. And then another example is machine translation. So an input could be like English text, and you have something like Google Translate, it will output the result. How does it sound like in Filipino or in the Cambodian language? So that's Google Translate is also part of machine learning. So okay, that's a bird's eye view of what machine learning is. But now we wanna tailor it to our use case of geospatial analysis. So because that's what this conference is about. So this is an example of land use, land cover application. So if you look at the pictures on the right, it's basically what it's trying to do is trying to classify what that area of land is based on the picture from a satellite. So as you can see, here's how grassland looks like. Here's what residential looks like. You can see they're clustered houses. This is how an industrial area looks like. Some of them are also highways. Some are just open water. And doing this kind of work is important, for example, for if you want to monitor how certain areas are changing over time. And also if you want to try to detect, for example, where are the rapidly urbanizing areas in a certain city. So you could classify, hey, maybe in 2023, now it's a industrial area, but back in 2018, they were just bare land. So that means there was a change in the classification, and there is some development there. So that's the use case of these pictures, and tying it back to machine learning. So how does a computer know that this is residential, this is industrial, this is grassland, right? And the way it does that is you give it examples of how grassland looks like, how residential looks like, how industrial looks like, and it will learn on its own without you having to explicitly tell them that, hey, if it's a bit greenish, maybe you could classify it as a grassland, etc. So if it weren't for machine learning, you would have done it like this. So you would make different kinds of functions to detect color, detect edges, analyze texture, analyze texture again, and that could be error prone because you don't actually know. There's so many different ways that the picture can look like. So what machine learning does is it removes this dependency on having to define all the rules when it comes to classifying images in particular, And what you instead do is let the machine figure out these rules on its own based on the data that you give it. Yeah, and so when it boils down to it, in machine learning, it all really relies a lot on labeled data. So when you have, for example, these pictures, and you tell the machine, hey, this is residential, this area is grasslands, you give it to a model, and then given once it's trained, you can give it a new image, for example, and then it can tell you, okay, so if this is the picture of that area, is it? I can tell you if it's residential, industrial, agricultural, forest, bare land, open water, etc. And it can even give you a degree of its confidence. So I'm 90% sure this is residential. That the model can do that. Okay, so that is in a brief overview what machine learning is. So does anyone have any questions on this overview of machine learning before we dive deeper? So any questions from the participants? Nope. Okay. Then one question here. Yeah, good.
Ba ជំរាបសួរខ្ញុំមានសំណួរមួយទាក់ទងទៅនឹង machine learning ចង់ដឹងថាតើmachine learning យើងគ្រប់គ្រងតាមប្រព័ន្ធ online ឬក៏យើងធ្វើជាឧបករណ៍ online or is it សម្រាប់វិភាគ
Sorry, we didn't understand. Okay, yeah, with headphones. Yeah, I think.
Yeah, I think the question was he want to ask if you will manage this by online or is it like a separate program to analyze all of this data?
Thank you. So thank you for the recap. So there are actually several options for machine learning. So there are machine learning models that are already hosted online. So these are some basic ones. So if you look at the common cloud platforms such as Amazon Web Services or AWS or Microsoft Azure, they have some machine learning models that can give you a prediction based on what it's currently, based on its specific use case. So for example, I do remember there is a Microsoft Azure ML model where you can give it a person's face and then it can tell you, hey, does this person look sad, looks happy, etc. And there are also there's a more generic service where you can upload a picture and it can tell you, is there a cat here? What kind of objects are there? Is there a chair? Is there a table, etc.? So there are those hosted models, but the thing is, it really depends on your use case. So you might, for your particular problem, there might not be an existing service out there for you. In that case, you might have to make your own one. So the answer is if it's hosted online or something that you have to develop yourself, then there's actually you can do both, and it depends on your use case which one is a better approach. So if your use case is relatively simple and there's an existing model for it, then of course you just use that, and then you just have to pay a fee for every time you use the service. But otherwise, you might have to build it yourself or hire someone to build it. So in the case of geospatial data, there's fewer examples of that. But yeah, I'll talk more about that a bit later. But I hope that answers your question. Do you have any follow-up questions? Okay. Okay. Right. Right. No other questions on what machine learning is? Thank you for that question, by the way. Oh, you have another question?
Hello. សូមអរគុណខ្ញុំចង់ដឹងថាដោយសារកម្មវិធីនេះយើងធ្វើនៅលើអនឡាញតើយើងអាច download វាជា pack មួយយកមក store នៅលើម៉ាស៊ីនលើ PC ហើយយើងអាច run បានដែរទេ Okay, thank you.
So if I were to repeat the question, the question is if machine learning models, is it something that you have to download on your PC and you can run it on your PC, or if you could run it on a cloud service, is that correct? Or you could host it somewhere else rather than just the PC? Did I get it right? Right. Okay. Yeah, you could also do it both ways. So so you could do both. And usually what we do is when you're developing a model, so if you're like a consulting team like us and you're working with a client and you're developing these models, usually you would do that on your own PC. And then, but it's also a mix. So the initial R&D, you would do it on the PC. And then when it's a bit more ready, you use the cloud to train these models, because these models need some compute power, such as GPU or graphical processing units. And after it's trained, you would, if you want other people to use your model, it's a good idea to host it somewhere when it's already ready. So yeah, there's many different options. So again, depends on the use case, but more usually you would use it on a local machine if you want to. You're still early on in development, but if you want to deploy it and have other people use it, then it's better to host it somewhere. Did I answer your question?
But សួស្តីខ្ញុំចង់សួរមួយសំណួរថាបើសិនបើយើងប្រើប្រាស់ម៉ាស៊ីន learning ហ្នឹងតើការចំណាយរបស់យើងគិតជាគិតទៅលើទំហំទិន្នន័យឬក៏ anyway តើអរគុណ
Right. So just to repeat the question, it was about the cost of how these machine learning models cost. And yes, that is a very good question. So we at Thinking Machines, we're consulting for a lot of clients who have a lot of questions of how to use ML or machine learning for their particular organization. And I'm sorry to say, but the answer is it depends. But I can talk about what are the big drivers of cost. So I guess the biggest driver of cost is the kind of problem itself and how easy or hard the problem is. So one way of gauging if how easy or hard a problem is if, at least for computer vision, if a person could do it easily, then a machine could also do it easily. So for example, one particular use case is if for example the problem is distinguishing between a picture of a cat and a picture of a dog, then if a human can do that quite easily, so a machine can also do that. But if there's some use cases that are a bit more complex. So for example, like self-driving cars. So that involves around a lot of a lot of factors, such as also like the local regulations on the roads, if there's a pedestrian, etc., and you're doing that in real time. So that's an extreme case of what a costly model can do. So what if you could simplify or have clarity about what the problem is, then usually the easier it is. So that's one thing, what the use case is in the first place. And then the second one is the data. How easy or how difficult is it to get data for your sample? So, for example, if it's something very obscure, if it's hard to get data for that use case in particular, then a model can't learn from it. So, what's one example? For example, if you're launching a new kind of business has it been released before? Let's say back in 2005, before the release of the iPhone, and you would want to predict how smartphone sales are. So there's no data for that yet, for what smartphones are. So you can't use a model to predict what are the sales of your phone if they don't exist yet. But however, for example, if you're talking about like satellite images, then that's a use case that's we have a lot of data of pictures around the world. So in general, the more data you have, the better. So that's one thing. And I guess the third thing that driver of cost is also really how, apart from just developing the model, how the stakeholders or how the organization even need what it takes to adopt that model in their work. So that's one of the things that it's quite that people don't usually talk about, because they usually talk about developing models, but what really matters is not just these models, but how these models bring value to the organization. And there are a lot of people that aren't used yet to machine learning, and it also takes some kind of like training or upskilling, or even just like these conversations on how we can make these models more relevant to and useful for the particular organization. So it takes also that extra legwork. That's not really technical; it's more organizational, I'd say. But yeah, we could talk more about this maybe after the workshop. So this is if there's a specific use case that you're thinking about, then we could talk about it. So okay,
For example, sorry, this might not be a very good example, but with a thinking machine, when we did the use case that we briefly did in the introduction, remember there's the irrigation schemes, crop yield estimation. It wasn't really a perfect, but it's sort of like an experimental thing. The cost-wise, we did the one survey, crop survey that typically we do. I said that there's a sample size of 390. This is a typical project, sort of a crop survey that we do. The cost of that, I think you should know better than I do. I don't know. It's the project budget. So that's that you think about a surveying, this household survey, 390, plus what we added was the geotagging of the plots, their plots. I think that was about like 5,000-6,000 with the group of all this PhD students and all this go around with the supervisor GIS specialist. So, and then plus we did the plotting of each of this individual plots in 160. Actually, that turned out to be the plot, what size was 37,000 plots from the sky. So that was about $6,000 additional. And then put them all together with the remote sense, the data sets and the data scientists. That's an additional part, but it really depends on how you want to predict the precisions. Data, but remember the data points is only 390. which is not a big data, right? But if you want to make it a little bit more precise, and I was told that is that you have to expand the data points, that's going to build up the cost as well, right? The survey cost will go up, and then you can do a little bit more sophisticated things. So this is a first trial. I don't think it's a very good example in terms of cost estimate, but as we get smarter, we can do a little bit more cost-effective things. Maybe just to give you the idea on what you really aim for versus what budgets you require. Sorry, just to add.
Thank you very much for that, Mijiko. And I think later on, we'll also talk about another use case that, so we talked about the cost of doing machine learning, but there's also the other side of what is the cost being saved when you use machine learning versus really doing a full census out there. So we have a use case later on, poverty mapping. So it's another one of our projects where you actually save money from using machine learning because you don't have to spend as much time and effort to do a full census. All right. So thank you for those wonderful questions. Now I'll be moving on to the next section. So here I'd like to, there are a lot of words. Basically, this is how a bird's eye view of how a machine learning project can generally look like. So we've broken this down into two main steps. So first is data exploration. Second is model development. So first is, so before you actually train the model, so that's the second part, there's actually a lot of data preparation and also even just defining the problem that you would need to do. So in the morning, I will be talking more about the data exploration side. So first is for any kind of project, really, even machine learning, it's often good to not just jump in right away without knowing what you want to achieve in the first place. So it starts really off with problem definition and really defining what's your metric that you want to predict. Is there what we call a dependent variable? This is the thing that we want to predict, and what is really the nature of the problem. So yesterday, if you remember, in the very first session, we talked about predicting rice crop yield. So that problem is clearly defined, where you have a dependent variable, which is the crop yield of a certain plot of land. And so that's a clear use case. And once the clearer this is, the easier everything goes. So we have experienced some organizations where, they hear about machine learning, but they actually don't know what to use it for. And sometimes that can waste some people's effort, because really you should start with knowing what you want to achieve. So, and sometimes there are some problems that may be too difficult. So sometimes you might have to redefine what the problem is. So maybe your metric is actually quite ambiguous even to the stakeholders. So you might have to clarify what your metric is. And sometimes you only find that out after some initial data analysis. So after you define the problem, you would find data relevant to your problem, and then check if the data is accurate, if there's missing data. And then we would do what's called an EDA, or it's a common abbreviation among data scientists for exploratory data analysis. So this is doing lots of plots, calculating metrics to see, just to have a sense of what the data is. And sometimes you find out that, hey, maybe there are really no patterns here. Maybe we should go back and redefine the problem. So I did mention that this is the workflow of a machine learning model a machine learning project rather. However, in reality, there's a couple of feedback loops or iterations. So maybe you're here, but then after finding out something, you would end up here. So it's not always a straight path. And that's because sometimes we're learning more about the problem after getting more data about it. But of course, it's always better to start off with a defined problem. Right. Sometimes when you do your initial analysis, you find out that, hey, it's actually not enough data here. You were trying to predict the rice yield. You want to predict the rice yield across Cambodia, for example. But hey, how come my data is just for this certain commune? Then maybe it's not actually representative of the entire Cambodian rice yield. So sometimes you find out that we need actually more data, and we have to go back to data wrangling. So what we mean by data wrangling is getting data from different sources and then putting them together before you do your more detailed analyses. And then sometimes, okay, so moving on to this right side, let's say you've put together your data and then you have made your initial model. So here in model design, you really think about how, because there's different kinds of models to choose from, and then you have to choose which one is appropriate for your data set and your problem. And after that, you would do basically what we call feature engineering and experimentation, which is basically tuning your model so that it predicts the right outcome. So it basically, refining it so it works well. Sometimes, and at the end of it, we have a step called model evaluation here, where we check the results. Is the model actually accurate? Can it actually predict rice yield in Cambodia? So sometimes after model evaluation, hey, actually it's a very inaccurate model, then you'd have to go back. Sometimes you go back all the way here and say we might get more data, but sometimes it's about the model. Hey, maybe the data is already there, but you just didn't use them correctly in the right way. So right now might be a bit theoretical, me talking about this, but later on, I will be giving a more specific example of how this workflow look like given a particular use case, so that hopefully it's also easier to understand. But yeah, bear this in mind. These are the general steps in doing a classical machine learning workflow. So yep. So yeah. Okay. Time check 9. So first off, before starting any machine learning project, you should know how to clearly define your problem and what data is relevant for your problem. So here I'd like to talk about a current project that we're doing at Thinking Machines. So this is a project with the UN. And so basically this project is about poverty estimation. So this is a project that we've had since I think 2018, and we've had different phases of this project. So it's a project that started with estimating poverty just in the Philippines, but the most recent phase of the project, we have expanded it to estimating poverty across Southeast Asia. So the main problem with this, the problem statement and use case is that, okay, we look at this map over here. So this is the map of the Philippines, and there are government agencies that report. So there's official government statistics on, let's say, the wealth of a certain area in the Philippines. And the way they do that is they we go and deploy people on the ground to have surveys. So they know their wealth, and sometimes they even measure it in different ways. So they would have a questionnaire on, do you own car? How is your house? How many do you have a TV? So they have a really detailed questionnaire, and they would also write down how your house looks like, and based on a scoring system, they could have a measure of wealth. So, and that's good. And that's very useful, of course. However, sometimes since it is costly to do these surveys, not just on a yearly basis, but also on a detailed basis, what usually happens is, let's say there's a certain region, instead of there's a certain region that you want to estimate wealth for. Sometimes there is a specific region that doesn't, you can't you can't you can't deploy someone to each household. So you can't ask a questionnaire to every single household. So sometimes these statistics are aggregated not at the more detailed level that other policymakers might need. So let's say within Phnom Penh, there is a government statistic on let's say the level of wealth, but sometimes you would need a more detailed, let's say per commune in Phnom Penh, what are the statistics? So that is the context of this problem. So without access to high resolution data, organizations can risk investing their limited resources in the wrong priorities. So this is what we're helping the UN DP with. So in this project, you can see the difference between just this map based on the government statistics. So as you can see, the more yellow it is, the more wealthy that area is. So in here, you can see the capital of the Philippines, which is Manila, which is the most yellow, and then some of the other regions are of a darker shade of blue. When you move here, this is what is generated by ML. The difference between this and this is that it's a bit more detailed. So instead of just having one color for just this general area, it's detailed per smaller area. So it's a bit more refined, and this kind of map can be useful for government and policymakers. So that was our challenge, and then how we addressed this challenge was we used machine learning along with open data sets so that we could make a map like this. And we used OpenStreetMap as a data set, and we used Python as our tool. Okay, so before moving on, does anyone have any questions on this use case and the machine learning workflow?
I just want to learn more about the poverty estimation.
Okay.
Maybe I can speak my good and English. ខ្ញុំចង់សួរអញ្ចេះតកតងទៅនឹង poverty estimation. The machine learning can evaluate the location of the people who live with the poverty. Or we need the data collection has to collect the data from the location where we need to collect, and then we enter the data to the program for the machine learning, or the machine learning can evaluate by themselves.
Okay, so just trying to recap the question. So the question is, how does machine learning get this data in the first place? So does it? Could you repeat? You said something about inputting the survey question somewhere and how.
Machine learning ហ្នឹងយើងអាចវាយតម្លៃថាប្រជាជននៅក្នុងតំបន់ហ្នឹងវាជាប្រភេទដែលប្រជាជនស្ថិតនៅក្នុងភាពក្រីក្រឬក៏យើងត្រូវតម្រូវការ data collection team ដើម្បីចុះទៅ collect data នៅក្នុងតំបន់ហ្នឹងដើម្បីបញ្ចូលទៅក្នុង machine.
Correct. Yeah. So yes, you would need data first. So before to input in the machine learning model before it could generate these. So in this use case, there was an existing survey called the Demographic Health Survey that is done across different countries. Also in Cambodia, there's also this survey. And in that survey, people really went out to different houses and asked questions. But they didn't get to ask every single person in the country, of course. So, however, the data of that is with DHS or Demographic Health Survey. And what machine learning does is it builds on top of the surveys that already been developed. So machine learning isn't a replacement for surveys, of course. We still need surveys because that is what is the ground truth, the raw truth. And what machine learning does is it augments that ground truth by making sure that we could have estimates for an even larger area and also for areas where we didn't have surveys for. So does that answer the question or?
But បានឆ្លើយហើយប៉ុន្តែខ្ញុំស្ដាប់មើលទៅ machine learning ហើយនឹង program ដើម្បី evaluation ដើម្បីទៅ evaluate ទៅលើ program មួយរបស់គម្រោង NGO មួយឧទាហរណ៍ថា NGO មួយយើងមានគម្រោងមួយដើម្បីពង្រឹងទៅលើភាពក្រីក្រអញ្ចឹងគេមាន program មួយ consultant ទៅមាន program មួយដើម្បី evaluate ទៅលើអាហ្នឹងអញ្ចឹង program ហ្នឹងហើយនឹង machine learning វាខុសគ្នាដែរឬក៏វាប្រហែលគ្នា
Yeah, so the program to evaluate poverty is different from machine learning because the program, I believe, if I understand it correctly, is they're collecting the data in the first place. So the data that's required for the machine learning is done by the program. Oh wait, I'm sorry. What do you mean by program? You mean a program as in a computer program or a program as in a government program?
We អាចជាកម្មវិធីរបស់រដ្ឋាភិបាលឬក៏ជាកម្មវិធីរបស់ NGO មួយឬក៏ស្ថាប័នមួយដែលគេបង្កើតឡើងដើម្បីវាយតម្លៃទៅលើស្ថានភាពរស់នៅរបស់ប្រជាជននៅក្នុងតំបន់ហ្នឹង
Yeah, so that's different from machine learning because the government program is there it's required so that we have the data in the first place. And machine learning it's a layer on top of that program. So it's not a replacement, but it will augment and amplify that program. So they're separate in that sense. Does that make sense? Or do you need more clarity?
No, I think it's about many of us do the evaluation of many of the government programs. Objective is something about the poverty reduction or income enhancement. So I think the question originated from whether this machine learning can be used for this. I think they started thinking in that way.
Yeah.
What I mean?
Yeah. So this is so that is actually in line with the goals of this project that we're talking about with the UN. So So yeah, machine learning can be helped to help that program by the government to reduce poverty. Although when it comes to the specifics, I think it will merit a more detailed discussion. But we'll be happy to take that separately apart from this workshop. So, but yeah, there are definitely opportunities to do that, and scoping it out is really part of the problem definition that we in thinking machines. That's a lot of what we do, scoping out the problem for a particular client and organization.
See, I think, Josh, I think this is very, very important for many of us.
Yeah.
To understand your explanation being, for example, you can't go visit, survey everybody, so you use the machine learning. The same thing applies for those who program who just needs to monitor and evaluate the impacts of whatever the investment do. Right? They do this, so they can't survey everybody. It costs you a lot of money. So there's a high expectation about, is there a role for the machine learning to play? Is there a way, the smarter way of collecting data sets to prepare for the machine learning to be utilized for the evaluation, evaluation? That's exactly what we are trying to do in a Rice SDP, for example. So that's a theme, major theme about many of the participants here. Just to add.
Thank you. Yeah. So yeah, it's really nice learning about your problems and your use cases. And I guess one thing to help with that is if how project evaluation and machine learning can help augment each other is at least for evaluation. If evaluation, so yes, you can't ask every household, but if you would if the way you conduct these surveys is that it's representative across the entire region and not just concentrated in just one spot, then that's actually a better that makes it easier to use machine learning instead of just surveying it in one area, putting all your resources in one area. So if it's distributed, it's much easier. But yeah, does that answer your question? Okay. So you have another question here? I have a couple of questions.
Hello. ខ្ញុំមកពីយុវដ្ឋានដំណាំឧស្សាហកម្មចង់សួរអំពីរឿង machine learning តាមការបកស្រាយ slide ខាងដើមមកឃើញថាmachine learning នឹងអាចទៅភាគពីភាពក្រីក្រមួយនៅប្រទេសហ្វីលីពីនmachine learning នឹងវាពឹងផ្អែកទៅលើកម្លាំងមួយចំនួនទៅ survey ពីរឿងប្រជាជននៅក្រីក្រនៅតំបន់នោះតើវិធីសាស្ត្រអីដែរដើម្បីឲ្យកំណត់ជឿជាក់នៅម៉ាស៊ីននឹងយកចូលជាផ្លូវការបានតើយើងរកវិធីសាស្ត្រស្អីដែលធ្វើឲ្យដើម្បីយើងចូលទៅនៃហើយចូលទៅ model machine learning ហ្នឹងបន្តមកទៀត output របស់វាមានកម្រិតជឿជាក់ប្រមាណដែរដែលអាចជាផ្លូវការបានសូមអរគុណ
Oh, that's a very good question, and that will be part of the exercise we'll do later rather. So but to answer your question quickly, well, number one, it goes back to the data again. So I'd say if the data sets that you would collect for your problem are relevant and good, then the better the model is. So that's part of here what we call model experimentation. So in this specific use case, okay, so for poverty estimation, we made that model more accurate by getting other kinds of different kinds of data sets together. So you do remember that we, for example, used OSM, and we could make a model that, hey, if there are many banks here, many restaurants, maybe it's a more wealthy area. But just using that in of itself, the number of restaurants, bars, banks may not be enough So we add more data set to better predict poverty. So there was a research paper actually here in the Philippines that, and our findings show that there's a data set called nighttime lights. So in a summary, that is basically a picture of the sky at night, and the brighter that picture is, then it's highly correlated to having higher wealth. So, and then when we added that data set alongside OpenStreetMap data, then it improved the quality of that model. So there are certainly different approaches to improve, and but I'd say that's the biggest factor, which is adding data sets that are relevant. Does that answer your question?
Hello, good morning everyone. ខ្ញុំសូមនិយាយជាភាសាខ្មែរបងខ្ញុំជួយបកប្រែសំណួរខ្ញុំគឺចង់សួរតកតងទៅនឹង machine learning នឹងដែរប៉ុន្តែខ្ញុំចង់ដឹងទៅលើថាតើ machine នឹងអាចធ្វើការវាតម្លៃទៅលើផ្ទៃដីដាំដុះដំណាំណាមួយនៅក្នុងតំបន់ណាមួយបញ្ជាក់ពីទំហំផ្ទៃដីហើយតាមទិន្នន័យដែលត្រូវប្រើពីដែលត្រូវដាក់ចូលនៅក្នុង machine learning នឹងត្រូវការប្រើប្រាស់ satellite ហើយនឹងត្រូវការប្រើប្រាស់គេហៅ survey data ហ្នឹងហើយត្រូវមកយកមកដើម្បីប្រៀបធៀបគ្នាដើម្បីកំណត់ភាពជាក់លាក់ណាមួយថាទិន្នន័យ data ហ្នឹងគឺអាច machine learning អាចវិភាគបានថាយកអាចកំណត់ថាបានថាយកយើងជឿជាក់បានកម្រិតប៉ុណ្ណាអញ្ចឹងណាហើយតាម machine learning ហ្នឹងអាចវិភាគថានៅក្នុងតំបន់ហ្នឹងដូចយើងដាំស្វាយហើយនឹងដាំស្វាយចន្ទីតើ machine learning ហ្នឹងអាចវិភាគបានអត់ថាតំបន់ហ្នឹងជាតំបន់ដាំស្វាយចន្ទីសុទ្ធឬក៏ស្វាយសុទ្ធតែអញ្ចឹងណាហ្នឹងហើយដើម្បីខ្ញុំចង់ដឹងថា machine ហ្នឹងអាចធ្វើការទៅលើការងារហ្នឹងបានអត់ហ្នឹងហើយone more question it's just not refer to our work but I want to know តាម machine learning ហ្នឹងមានចូលទៅក្នុងការប្រើប្រាស់ហើយ security នៅក្នុងទូរស័ព្ទពេលយើង scan មុខមកវា auto lock សោយើងតែគេប្រើអាហ្នឹងអត់ខ្ញុំចង់ដឹងអាហ្នឹងដែរ that's all.
Okay. Wonderful questions. Thank you. So I guess I'll answer the easier question. Is it machine learning being used when I'm unlocking my phone right now? Answer is yes. Yeah. So Apple or whatever device you're using, it is using a specific type of machine learning, which is computer vision, which is also specific to your face. So what usually happens is, I think at the start you would scan your phone and then the phone knows how you look like, and then there's a model that can say, hey, yes, it's you or not. Okay.
So just to add to that, when you mentioned security concern that you hold your phone a lot and it uses a lot of machine learning applications, so that's actually where open data restrictions comes in. So a lot of technology companies are restricted from using personal information gathered through phones, for example. So they are not allowed to share that to other companies or other agencies, as well as they are not allowed to use it outside of the designated purpose of collection. So for example, when you scan your face, when your phone scans your face, the phone companies are not allowed to save or record that data because of these policies and restrictions.
Yes, if it's saved, it should. I'm not fully sure of the Apple terms of service.
Sorry.
Okay. I'll answer the other question first on, can machine learning be used to detect what kind of crops are in a certain area? And yes, that's something that we've been hearing about as well from another client that we've been talking to. But yeah, that's a common use case of satellite imagery, actually, crop detection. Although it will also depend on the kind of crop and how easy it is to distinguish from satellite imagery. But the short answer is, if a human can easily distinguish it, on this type of satellite imagery, then a machine can also do it. Because we've also had a request before, hey, could you help detect seaweed, for example, from satellite imagery? But that's underwater, so we'd have to say, hey, maybe that would be more difficult, but maybe coconut's easier use case.
Yeah, so just to add to that, it's very common use cases in the agricultural sector to use machine learning to, for example, count trees, classify what type of trees they are. Are they fruit-bearing trees, such as, so for example, in the Philippines, we are trying to develop a program to count and identify if the trees are banana trees, calamansi trees. So these are some local agricultural trees that we plant across the Philippines. And yeah, so we are trying to use machine learning to monitor and really help the agricultural sector with that. Sorry. Just one, maybe just two more questions before we go into the break. Sorry. Yes. Sorry, what was the question?
Is it possible to measure crop yield accurately?
Yes. So with regards to your question about accurately measuring crop yield, the answer is yes. So evidently, model accuracy is really dependent on the quality of the data you use to train your model. So the better your data is, the better your model will perform. So that's one factor. So there are already a lot of past researches and work that have created crop yield estimation models with higher accuracy, but these actually use quite very organized data sets. So once you build your foundations with how to collect and organize your data, and then that's when you can actually build better models to predict yield.
But សួស្តីខ្ញុំមកពីការឡៃកំណត់ដំណាំដុះកសិកម្មហើយខ្ញុំក៏ចង់ចែករំលែកបទពិសោធន៍ពីការធ្វើផែនទីដំណាំជាមួយនឹង machine learning ដោយសារខាងការឡៃឬក៏យោធាយើងកំពុងតែចាប់ដើមធ្វើ crop mapping ជាមួយនឹង machine learning ដែលយើងផ្ដោតទៅលើដំណាំស្វាយចន្ទទីហើយសម្រាប់ការធ្វើចន្ទទីរបស់យើងផែនទីចន្ទទីរបស់យើងហ្នឹងគឺយើងប្រើ machine learning ហ្នឹងតែប្រើ model ខុសគ្នាពី random forest ពីខាងស្រូវយើងប្រើជាលក្ខណៈ conservation neural network អាហ្នឹងធ្វើការពិភាក្សាទៅលើ texture ដោយការប្រមូលទិន្នន័យរបស់ពួកយើងហ្នឹងយើងប្រមូលទិន្នន័យលើក្នុងមួយ plot ហ្នឹងទំហំ4គីឡូគុណ4គីឡូដែលយើងប្រមូល detail ទាំងអស់ថាក្នុងទំហំ4គីឡូគុណ4គីឡូហ្នឹងគឺមានស្រូវមានស្រែមានភូមិមានដំណាំអីទាំងអស់យើងប្រមូលដោយធ្វើការ digitize ដោយដៃហើយបន្ទាប់មកបានយើងយកជាមួយមក run ជាមួយនឹង machine learning របស់យើងហ្នឹងហើយហ្នឹងហើយក៏យើងអាចធ្វើការកណនាផ្ទៃដីដាំដុះរបស់ចន្ទទីឬក៏យើងអាច apply ហ្នឹងទៅលើស្វាយឬក៏ដំណាំផ្សេងៗបានអញ្ចឹងបាទសំខាន់ក្នុងការធ្វើដំណាំយើងប្រើ model ផ្សេងគ្នាបាទ
ឆ្លងតាមការរៀនសូត្រពីក្រុមការងារយើងដែលបានសួរសំណួរក៏ដូចជា facilitator ដែលគាត់បាន facilitate នេះខ្ញុំlearnបានថាlearning machine estimate ទៅបានសុក្រិតគឺអាស្រ័យទៅលើ questionnaire ឬក៏ data collection team របស់យើងថាតើយើងចុះទៅ collect data ហ្នឹងបានសុក្រិតប៉ុណ្ណាហើយ questionnaire ដែលយើងបង្កើតឡើងតើវា respond ទៅនឹង objective ដែលយើងចង់បានដែរអត់ឧទាហរណ៍ថាពីមុននេះ facilitator គាត់បានមានប្រសាសន៍ថាmachine learning estimate ថាតំបន់គោលដៅហ្នឹងគឺជាតំបន់គោលដៅដែលភាពក្រីក្រប៉ុន្តែប្រសិនបើ data collection team ចុះទៅ collect data នៅតំបន់ហ្នឹងมันបានសុក្រិត នោះក៏វាមិនអាចឆ្លើយតបទៅនឹងតម្រូវការរបស់យើងហើយ learning machine ក៏មិនអាច estimate ត្រូវបានច្រើនដែរវាអាចមានកម្រិតលំអៀងខ្ពស់ដែរបើអញ្ចឹងគឺអាស្រ័យទៅលើ questionnaire របស់យើងដែលបង្កើតហើយនឹង data collection team គាត់ understand the purpose and the objective របស់យើងនោះប៉ុណ្ណាបាទអរគុណ
Yes, thank you very much. That is a very excellent summary, actually, of how machine learning and these surveys can work hand in hand. So, yes, data quality is very important. So, thank you very much for that. Was a very excellent summary.
Hello, ជំរាបសួរបាទនេះជាសំណួរទី2ខ្ញុំចង់សួរថាmachine learning ហ្នឹងវារត់ទៅលើរត់ជាមួយនឹងផ្កាយរណបឬក៏វាមានកម្មវិធីអីសម្រាប់ដំណើរការវាដោយមិនបាច់ពឹងពាក់លើផ្កាយរណបហើយតើសម្ងាយនេះផ្កាយរណបប្រទេសមួយណាដែលរ៉ាន់ជាមួយនឹងម៉ាស៊ីនហ្នឹងហើយតើហានិភ័យវាថ្ងៃក្រោយបើសិនជាមានបញ្ហារវាងប្រទេសទាំងពីរហ្នឹងវាអាច error យ៉ាងម៉េចឬក៏មានបញ្ហាយ៉ាងម៉េចបាទសូមអរគុណ
Yeah, so first question I'd like to address is do you always need satellite imagery to do geospatial data analysis and models? So the answer is actually no, you don't always need satellite imagery. So actually this is an example of that. So in the first research paper for the Philippines, we actually did two types of models. One model that uses satellite imagery in the model to predict the wealth, and another one that doesn't use it. So actually the one that doesn't use satellite imagery performs just as well as the one without, and it's much easier to use as well. But of course, that depends on the use case. For this use case of poverty, we found out, at least in the Philippines, we found out that you don't need satellite imagery for that. But there are other use cases, such as if it's very dependent on how the area looks like, such as crop mapping. That is where satellite imagery is more relevant. On the question on dispute between different countries and on data sources, when it comes to satellite imagery, I'm not very aware. I haven't heard of any dispute between countries because usually satellite imagery comes from across. There's usually one provider that does it across the entire world. So, for example, a commonly used satellite imagery is Sentinel-2. So, Sentinel-2 is deployed, I think, by a European agency. And that European agency collects data across the world. So there might be more niche or specific satellites that only use data from one country, but monitor one country rather. But more often than not, there's usually worldwide coverage for the most popular satellite imagery providers. So there are also private companies such as Maxar that provide high resolution satellite imagery across the whole world. But that also, you would need to pay for it more. In terms of dispute between countries on not satellite imagery, but just data, at least for data sets like OSM, maybe it's less of dispute, but more on the level of engagement of the open source community behind that data set. So, for example, OpenStreetMap is a data set that where it's like a Wikipedia of maps. So it's where people upload and map out their specific areas. And it's not that it's disputed, but rather there are some countries where there are more volunteers than others. So there are countries that are more mapped than others. So, for example, Philippines, we found out that the open source community in the Philippines is active, so there's more data there compared to, I think, Indonesia. Indonesia has a lower number of contributors. So there's multiple answers to that, but I'm not really sure if there's a really dispute in this case. Does that answer your question? And I think after closing this one, we'll move on to the next. Or maybe we'll have a break. I think it's already 10:10, so might be time for a break. So yeah, if no other follow-up questions, I think we could have a break. Thank you all. And we'll resume in I think 15 minutes. Oh.
Maybe you can explain about whether you can tree classification actually done in a forestry in crop. That's very new to me. So maybe you can clarify that. Sure. It's evolving area.
Yes.
We haven't done that, especially in India, because it's not really
right. So thanks for bringing that up. So Michiko was just asking for more clarification with using machine learning in forestry and agricultural applications. So some of which I think we can add a few slides if we have time left in the sessions later. But we did do a machine learning model to classify and detect drivers of deforestation. So in the Philippines, we do have a lot of causes of deforestation, such as local practices of slash and burning. So it's typical, more similar to forest fires. There's conversion to agriculture and all that. So we actually used a machine learning model to identify where there are areas of forest loss and also look into what caused this forest loss. Another is for agriculture. So this is actually an ongoing development for us. It's really using satellite images and machine learning models to so initially we are counting trees. So this is for a mangrove restoration project. So for those unfamiliar, mangroves are these very beneficial trees that grow in coastal areas. It protects the areas from storm surges and other weather dangers. So we in the Philippines, we really do focus on restoring them, as well as it offsets a lot of carbon. It's good for climate change. So yeah, we're also working on machine learning models to detect these trees, count them, and also monitor their growth, so that it informs these organizations that do the restoration on how effective their programs are working.
I know what I meant was you mentioned about the tree.
Yes.
And then when it comes to agriculture, the cost, sorry, just to ding on this is very important for the agriculture people. For example, machine learning prediction of the weather and what's going to happen, and best maturity of the tree crop, for example, before the rain comes. This is very critical for the harvester to have that maximizing the profits, right? And then when you try to predict that and detect which trees is the mango trees, which trees is lychee, which trees is the guava. In India, for example, it's not really predictable to say exactly. I mean, ground observation you can do from the sky and machine learning. Our understanding being that it's not really practical exercise to detect the detail exactly where just crop areas and what trees, what is the maturity, and so that sort of detail, sort of classification of trees. Same goes for this forestry composition. This is a few years old. The Google forestry sort of training was mentioning that you really have to combine the ground level truth to really detect exactly which tree species are growing and monitoring. So that's the clarification I wanted to have. Then I would like to talk to you later about this, exactly how you monitor that too. Sorry.
So exactly. Ground truth is still very important in these tree detection activities. So it's important to note that the more specific or the more precise information you are trying to predict or estimate using machine learning, that also equates to more difficult problem in development. So it's a bit more experimental. But Michik, as you mentioned, this was a problem that you encountered a few years ago. There has been some recent developments already in technology that is making this the more detailed data sets as well as the more powerful models to actually be capable to already do these types of classifications. Though it's still very early stages development, but there has been a few researchers that were able to do it. If I Most of them actually use drone images, so they're more high resolution images than satellite data, and so you can get a clearer view into the area, and as well as it also requires a bit more specific surveys. So part of the mangrove restoration, mangrove monitoring model that we are developing, we actually went into mangrove forests and individually measure the trees of their height, of their how big the trees are, what the species are, and that's what. So it's really very detailed data sets used to also train these very detailed models. So, but of course, it's important to note that this increases the complexity of the model as well as the difficulty in having the model more accurate.
Thank you. So, right. Yes.
Yes.
Great. Yes.
Yeah,
We can
10:30.
come back at 10:30 if that's okay. Thank you.
Thank you very much.
Yes. Thank you. Yeah.
One, two, three. 1, 2, 3 អត់លើ
Hello, hello. 1, 2, 3. Test, test. Hello, hello. 1, 2, 3. 1, 2, 3. អត់លើដែរ Hello, hello. 1, 2, 3. 1, 2, 3. Hello, hello. 1, 2, 3. 1, 2, 3. លើ Hello, hello, hello. លើ
Yeah, we never downloaded. Okay, so first try it out. That's you guys that so these can break, after that. Aggregation then will require On the way forward, and the next one will be and that's really terrible yesterday. Maybe after the next two of what what I mean, you have to find the what's the next step. All you have to do is over for us. Yeah, yeah. Thank you.
Morning, everyone. Let's start soon. Now we'll be moving on to a more technical session. So let's just wait a minute for everyone to settle in. So you might want to bring out your laptops and connect to the hotel Wi-Fi because you'll be needing your laptops for this time of the workshop. Huh? Bakit? Mahina ba? Ah. Oh yeah. Okay, I think we can start. So yeah, good morning, everyone, and thank you for the lively discussion earlier. So we really appreciated all the questions coming from all of you. So just to continue the presentation earlier, so we did talk about how important it is to define your problem first, your use case, and have a conversation of how machine learning can help before diving in deeper. Now that we've introduced this specific use case of poverty estimation, we can start with an exercise of how we actually did this. So again, a bit more context, a bit more detail. Now, from our previous poverty mapping project in 2020, actually it's 2020, since 2022, we've been working on scaling out this process, not just for the Philippines, but across Southeast Asia. So we are going to tackle actually this use case of poverty mapping, not for the Philippines this time, but now for Cambodia. And of course, this will be an example. This won't be the full exhaustive steps of how you would do it for a real project, but I hope this will get all of you to be introduced to the general workflow, even if it's not the full comprehensive workflow. So we trim down the section so that it's a bit more easily understood. So, okay, so what do these things on the right side mean? So again, remember that in poverty estimation, we started with the survey questionnaires collected by the DHS, or Demographic Health Survey, to map poverty across the country. So this is a general summary of how we developed the model. So there are different kinds of data sets that we could use to predict the wealth, such as OSM, such as nightlight. So there's a bit of experimentation or trial and error of finding which kinds of features or data sets are relevant to predict. And there's also what we call hyperparameter tuning, which is tuning the model itself rather than the data set. And then we then think about how to roll out that trained model across the entire country. But we'll get into these details, I think, more in the afternoon. So right now, let's start from the basics. Let's start from understanding what our data sets are. I hope you could join me now in opening this Colab notebook. So don't worry, Google Earth Engine isn't required for this time. We'll be using mostly files from Google Drive. So I hope all of you could go to this link, bit.ly ADB classical ML walkthrough. So I will walk with you step by step of how we are going to do a poverty mapping model for Cambodia. All right. So if we were to do this, so step by step, go to this link. Okay, so some people might still be setting up their laptops, so could wait a bit. But oh, sorry. So okay, maybe flash the link here first for a while. Yes, and sometimes I do use poverty mapping and wealth estimation interchangeably, but right now let's call it wealth estimation. So sometimes poverty mapping is what it was called by our correspondents with the UN, but I think in this case we could call it more wealth estimation. So first, if you're here, let's do the first step of making a copy. So wait, I will go to my email account first. So wait, oops, not this one. So I'll just change this to the thinking machines. Oh. Oh. Wait, let me do that again. This one. So let's wait for everyone to get to this link first before we move further. So is anyone can everyone raise their hands who has successfully went to this link? Okay, so people in the middle still need some time. Okay. So let's wait a few more seconds. And my colleague Ren will be moving around for any kind of technical assistance. Okay, so the first thing, if you're already on the Collab notebook, what you could do is the first step. It's make your own copy. So you go to File on the upper left, and then click Save a Copy in Drive. So this will make sure that your changes are just reflected on your own personal copy, and that because the original file is the master copy that's seen by everyone else. So you would see this creating a copy on the lower left. So let's wait for it to make a copy. Taking a while. Okay, this. Okay. Let me do that again. Oh, there we go. I just took. Is everyone using the same? All right. Yeah, that's true. Everyone's using the same internet. Okay, same Wi-Fi. Okay, so I hope since I'm also using the same Wi-Fi, and then I will go at your pace. Okay, so everyone, raise your hands if you've already created a copy. Okay, so let's start. So like yesterday, this is a Collab notebook where we do all of our data analysis on a browser. So first step is we do is click connect here. So you could start the running programs on the Collab notebook. So here it's connecting, initializing. Okay, so now it's connected, right? So here we'll be doing wealth estimation. Okay. Yeah, wealth estimation. Right. So we'll be tackling just the first section here. There are going to be 3 exercises, but before lunch, we hope to at least complete the first section. Right. So, right. You can read this in your own time, but basically the goal of this notebook is to provide a wealth estimation model based on VHS survey data, which uses the following data sets from open data. So nighttime lights, OSM points of interest or POIs, and internet speed data from Ookla, right? So first we could do is, again, do the setup. So you've been seeing this even yesterday. And this is a necessary first step to install the Python libraries that will enable us to do the kinds of processing that we need. So it's really, if you can see, it's downloading and lots of libraries from the internet. All right. And when you see this check mark on the left side, it means it's done. And then now after we've downloaded them, it's now importing. So what it does is the libraries that we installed, we will import them now in our notebook. So we could use these functions. So as you can see, there's a lot of functions that we used here, but we will answer them or explain them as we go. So now it's checked, they're imported. Okay, so first thing is downloading these data sets. So as you can see, there is a data set here called the Cambodia Administrative Boundary. So we could get that data set from this link, using this link. So if you just run this cell, it will download the data. And remember, you could either click this to run the cell, or you could also do Shift plus Enter to run the cell. Then we can download the DHS survey data. And I guess one thing I'd like to point out about the DHS survey data is you would actually need permission from DHS to use this data set for your own use case. So right now before this workshop, we sent a request form for DHS so that we will be able to use this data set for this workshop. But we hope that you won't have to. Okay, I think Ren can explain this more.
Hello. So since we are using DHS wealth index datasets, we did submit a request to USAID to access this dataset for the purpose of this training. So outside of this training, please do avoid using it out for other purposes. If you do intend to use it for something else aside from this training or working on this notebook, you can submit a request to DHS itself, so it will be linked in the materials that we will be sending to you. So you can request it for yourself and use it for the project that you intend to use it in. So thank you so much.
Yep. So this is the DHS survey data from for Cambodia. And next week we will download nighttime lights. Oh, I think there's a question here.
សូមអរគុណខ្ញុំសូមនិយាយភាសាខ្មែរបាទចង់សួរតើតើចំណុចកុំនី DHS ហ្នឹងយើងប្រើបាននៅក្នុងអំឡុងពេល training អញ្ចឹងពេលដែលចប់ទៅ processing ហ្នឹងតើយើងអាចមករ៉ានសម្រាប់ទាញយកទិន្នន័យហ្នឹងយកមកសិក្សាបន្ថែមបានដែរអត់
So for this notebook, you can use it as a reference, and you can also use it for your for personal learning. We will be sharing it to you as additional reference for this workshop later on. But if you intend to use it as an example, for example, in your own organization or ministry, to share with your group, we'd like to suggest that you request for the DHS data yourselves instead, rather than using the ones used here. So after this workshop, we intend to remove access to the DHS data that we are downloading here, just so we are able to comply with the use conditions that are employed by USAID. So they're the providers of this data set, and they have very strict user conditions.
Yes, but I think if DHS will be able to grant access to you, and if you want to use this notebook, you can. So you might just have to import it in this notebook in a different way. So instead of downloading it from this source, you could probably host it in your own Google Drive and then download it from there. So yeah, there's you could do you can still use this notebook, but you just have to request the data set separately and host it separately.
ASEAN ខ្ញុំតាក់ទងជាមួយនឹងវិស័យទេសចរដែលយើងត្រូវទាញយកទិន្នន័យសន្តាគារពីGoogle Code ពី Agoda ហើយនឹង Booking Online អញ្ចឹងក្នុងអំឡុងពេលដែលពួកគាត់ training ហ្នឹងទិន្នន័យហ្នឹងគឺ code ហ្នឹងយើងទាញយក process បានដែលទាញយកទិន្នន័យសន្តាគារតាមខេត្តមួយតាមតំបន់មួយយកមកប្រើតែបន្ទាប់ពីចប់រយៈពេលប្រហែលជា6ខែក្រោយមកយើងយកអា process ហ្នឹងដើម្បីយកទៅចែកចម្លែកនៅក្នុងការ training បន្តសម្រាប់ស្ថាប័នពាក់ព័ន្ធរបស់យើងណាបាទចាំបានមកហើយយើងបាន reply ទៅជំនាញដែលគាត់បដិបដាយើងហ្នឹងគាត់ថាមកពីយើងហ្នឹងយកច្រើនពេកដល់ពេលអញ្ចឹងអាកូនហ្នឹងយើងចង់យកមកប្រើប្រាស់បន្តទៀតសម្រាប់ training បន្តទៀតគឺមានសិទ្ធិភាពបាទហើយគឺ process គេគឺគេ process code ជាមួយនឹង collab ដូចគ្នាគាត់ថាមួយវាប្រើតាម website web scraping ពី Agoda ហើយនឹង Booking បាទអរគុណ
So thank you for that question. So I'd like to clarify for this notebook, it will be available for everyone's reference, even outside of this training program. If you would like to use the data to rerun this by yourselves, then yes, you can still access the data. But if it's for the purpose of, let's say, you want to use it as an example to train other people or use the data set itself in a different program or application, then that is what's not, prohibited from prohibited use. If you do intend to use it for a different program or a different project, I'd be more than happy to assist you with submitting the request for the DHS data.
Yep. Yep. So if it will be okay, let's proceed. And if there are other questions, maybe you could just have it with okay. Last question.
អរគុណចំពោះនៅ data CDS នេះតាមដឹងគឺដាក់ release ជាសាធារណៈបីថាជាទិន្នន័យដែលគេបានសុំការអនុញ្ញាតតើវ៉ារបលណាដែលត្រូវដាក់ផ្សព្វផ្សាយវ៉ារបលដែលត្រូវការអនុញ្ញាតអញ្ចឹងបើសិនជាទិន្នន័យនេះជាទិន្នន័យគេផ្សព្វផ្សាយសាធារណៈខ្ញុំគិតថាអត់បញ្ហាទេលើកលែងតែវ៉ារបលមួយចំនួនសូមអនុញ្ញាតអានេះដាក់
Yes, yes. So actually, most of these data sets are open. It's just that the DHS is the only data set that does have a terms of use restriction. But yeah, agree with what you said. Okay. Okay. Will it be okay to proceed? Okay. So now we could. And if you have further questions, you can approach Ren separately. Who's there? Okay. Now for the nighttime lights, you can download it as well. So right now we provided it as files on G Drive and you just use this code snippet to download them. Yeah, and then now we do some more setup, basically making a directory for all the data sets. Right. Now, moving after downloading, let us start understanding each data set. So first, we'll be looking at what the DHS data looks like. So we've downloaded it, we've been talking about it, but this is how it really looks like. So this is how the DHS data looks like. If you run this cell, you would see this table, and it says that there are 611 clusters. So DHS, what this means is that they've surveyed 611 households, and DHS comes with a wealth index. So each cluster, let's say cluster 1 or from 2014. It has this wealth index of -7,443. And it's a good question to ask. What does this number mean? Is it their average income? Because negative doesn't make sense. You might wonder. And actually, it's a bit technical why it's like this. So they've constructed a metric to compute the wealth index using other answers in the survey, such as I think it was income, let's say number of cars, etc. So they constructed a wealth index based on a technique called PCA. So this number doesn't actually represent a physical thing, but rather it's more of a overall summary of how wealthy this household is based. And if the number is higher, it means it's more wealthy. If the number is lower, it means it's less wealthy. So yes, you can just interpret it as an index rather than a representative of actual income. And you have a geometry data set here, or geometry field rather, and it tells you the coordinates of where this household is. And one thing to note with DHS is that they've also been keen to protect the privacy of the household respondents, because wealth of a specific household is also like sensitive information. So what they've done is actually to so these aren't actually the exact coordinates of the household. They have jittered the coordinates a bit. So they've made sure that this isn't the exact area, but it is within a certain radius of this area. So so this is our primary data set, which thanks to ground survey we've collected. And next we convert this. So we have a string representation of this. So it's just a technical detail. And next if we run through this, one of the first things we will do is create a circular buffer around each cluster centroid. So basically, remember here, you have a point. We'll make a circle around that point that is 2 kilometers big. So again, here we run into the CRS problem again, and we have to change this to a Cambodian CRS and EPSG.io. So if we go here again, we could search Cambodia. Cambodia. And I think yesterday we used this one, WGS 84. So we'll be using this projection system so that we'll be able to interpret our units into meters, right? So this one. And the reason we had to do this one is because we're using a buffer. So remember, originally the units of this are in degrees, but if we want to make a radius, we have to convert it to meters. So 2,000 meters is 2 kilometers. And then, yep. Let me just rerun this to make sure it's correct. All right, so okay, so here, if you can notice, the geometry is now a polygon instead of a point. And one way to do that is to visualize it. So DHS, oops, not there. Actually, it's been explored here. So you could use .explore to visualize how it looks like. And as you can see, these are the 611 survey respondents. And we made a 2 kilometer buffer around each of them. See, so So is everyone here on this step? Could you raise your hands if you've reproduced the same result on your own Colab notebook? Okay. So yeah, this is one way to, the first step is to just do an EDA or exploratory data analysis just to see how your data looks like. And if you've noticed, there are more survey respondents here versus in other regions. Maybe it's because there's less population in those areas. So yeah, going back to the slides. Yeah, so data wrangling. Just get one of the goals is just to get an overall feel of the data, see if it makes sense, and that involves visualizing it. And okay, maybe I can go here first. So we'll talk about OSM here, OSM again, and later we'll talk about satellite imagery. So yeah, this is again how the DHS data looks like. Rough index, not long, and then we'll talk about OSM in a bit. Okay, so now we're here. Next is UCLA. So I think this is a good data set for measuring the internet speed in a certain region, because I think high internet speed is also correlated with higher wealth. So UCLA has a open data initiative to release a data set of internet connectivity across the world. So see, here's a map on their website. And however, the processing this data set does take some work. So we've written down some code for you to be able to easily process it. So right here, for example, we are downloading the internet speed for 2019 Q1. So you can just wait for this to run. Yeah. So and then we've written some functions to just load the UCLA data. And yeah, let's wait for this to run. This takes 5 minutes to load because it's quite a heavy data set. And while we're waiting for it to load, maybe we could go through the UCLA website. So you might want to consider this for your own use cases, especially when it comes to wealth estimation, or maybe even finding out which areas in Cambodia need help in terms of internet connection. So here we could zoom in. Let's say go to Cambodia. So you can see that the more you zoom in, the tiles become also smaller. So they've aggregated this data set in various levels. So Phnom Penh here. So you can see if you were to interpret this chart, this is mobile internet, and the darker the color is, the faster the internet speed. As you can see, the center of the capital, it's darker compared to the outskirts. And you could also check this between mobile and fixed. I think fixed is like broadband internet. So generally the same. You can see that it's the fast internet speeds greater than 250 Mbps are here in the center. And you can zoom out to see other areas. See in Siem Reap, there's some areas with internet, high internet speed, but there are areas outside where there might be no data because people don't use internet or have a speed test in those areas. So that was for fixed internet. This is now for mobile. So feel free to go to the UCLA website to see the data set for yourself. And we can go back here. Okay, it's still loading, 5 minutes. Yeah, on this, maybe, does anyone have any questions when it comes to the data sets? Oh.
Just about internet.
Yeah.
What was the square? I wanted to understand this one, yeah. It's just province level, maybe? See how at national level you can see, provincial level you can see. Maybe that's the best. You know, it's really great, isn't it?
Yeah. Yeah, so I think so it's based on Ookla's tiling. So I think what they did is the size of the square is dependent on your zoom level. So if you zoom out, it will just give a general summary within this square. But if you zoom in, it will be more detailed.
I'm just thinking about this. This could be a good alternative to the nightlight.
Yeah.
Especially in the rural area.
Yeah.
But if you find like a green, then you can't really use it at the small district level or communal level. If that can be done, that's super.
Yeah. I think what's happening here really is that the raw data is at a detailed granular level, and it's just Ookla that's summarizing it at the large area. So that's one thing we'll be doing here, is to summarize this data based on these circles instead of these squares. So that's one of the exercises here. And in terms of nighttime light and Ookla, we're actually using both in our data set, and we can see later which one of them was the better predictor of wealth. So you can use them both. And as you can see here, there's two numbers, average D and BPS and U. So these are download speed and upload speed. So when you do a speed test, usually both are reported. All right. So from there, we could also explore the Ookla dataset that's already been pre-processed. So you can see it's aggregated at this. I think this is the smallest square of aggregation by Ookla. So as you can see in this specific square, this is the Mbps 5.3, Mbps download 1.3, Mbps upload speed. And you can also see the number of tests made in that area within that time. So 105 tests. And you can see how this table looks like. So a quad key, it's basically a unique ID of a box. So this box is this, and then the one next to it is 3. So you can see the last digit is 2. And then after this, the last digit is 3. It's because they're next to each other. So there's a tiling system based on this. And then for each tile, there's the speed, device, and the polygon. So sometimes you have some tiles that just have been tested once. So maybe those are less accurate compared to other tiles that have had more devices. But yeah, this is also just based on one snapshot. So you could also check across a larger time span, and maybe there are more data points. And next, we are downloading and processing OpenStreetMap. So OSM, we've seen this yesterday. Okay, so here we've gotten OSM data points. So this is yet another data set. We're done with UCLA, we're done with DHS. Now we're downloading and processing OSM. So just like yesterday, they've been bars, banks. Now you have supermarket and cafe. And these are their coordinates. All right. So yeah, a lot of this was checking the data. So it's a very crucial part in any machine learning project. Just does it make sense? Do they fall within expected ranges? Are there missing values? Are there areas that are not really represented? For example, there are no speed tests in this area. It's not that there's. So yeah, maybe that's also a factor. Right, and then let's just have time check. It is 11:20. Okay, I think we could finish this section. Okay, so now that we have our data sets ready, we do what we call is feature engineering. So remember, going back to our problem statement, this is about wealth estimation. And in terms of wealth data, what we have are circles. We made circles around each DHS cluster. We made 2-kilometer circles. So, okay, so now what we want to do is to create statistics for each circle using the different data sets that we have. So first using OSM. So we have OSM here. Okay, we could plot it again just to see for everyone's benefit how it looks like. So if you explore, okay, maybe you wanna, oh, no. Maybe this is a lot. Oh, yeah, so there's a lot of data points here. It might take a while to load. So maybe you could just use dot head just to see the first 100 rows. Okay, so this will be faster to load on the map. So the first 100 points are here. So you have a, I think this is what's this? It is a car dealership, for example. So they have these points, and what you want to do is remember the DHS clusters on here. These are circles, and what we want to do is to count how many points are inside each of these circles. So how many car dealerships are within the circle? How many restaurants? How many, etc. And you do that for every point, every circle here. You count all of the points. And that's one way of measuring the wealth. So, hey, maybe there's a hotel or a hotel next to this. Maybe it's higher of a higher wealth versus another area that doesn't have anything. So that's what we'll be doing in this first section of feature engineering. So feature engineering is that general term of creating statistics for predicting your target variable. Right. So here, as you can see, we have each cluster again, each with their own circles, geometry, and now we made a lot of statistics based on just a few POI. So we have within the circle, we have 5 points. And then of those 5, 2 of them are schools. And I think they're the other ones. I think there are other kinds of points that were included. Yeah, because we specifically we're just specifically counting these types. So the other points are other. And you could change this function so that we could read different kinds of points. But I think to make the processing faster, we're just limiting ourselves here for now. Yeah, so you have 5 points, 2 of which are schools, and then the other 3 are of other types. And then the nearest restaurant is 200 meters away, 100 meters away, etc. Wow. Sure. Yes. Oh yeah, good. Me and siya.
4026 at iba yung
Binalik ko siya.
No, pero okay.
Yeah.
Gotcha. No, the yung may selection is not conclusive.
Yeah.
Yeah.
Yeah, so just also make sure that right now all of our data sets are in this projection 4026, and 4026 is the most common projection, which is just latitude longitude. So right now we made the circles, we first projected it into Cambodian CRS. We've made a 2-kilometer buffer, but we put it back to 4026. So for majority of this analysis, we'll be working with 4026. Okay. So yeah, just going back to this table, you can see, and we have another cluster where the nearest restaurant is. We put a placeholder value of 9999. If you couldn't find the nearest restaurant is really far away. But yeah, so these are all the statistics. And with this, you could actually make a model with just this data set, a simple model at that. But yeah, you could predict the wealth given the number of restaurants, bars, and how near they are. Or rather, restaurants, schools, how near they are, etc. And now you can do the same thing for the UCLA data set. So again, it's the same story for each circle. How is the internet speed? What is the average internet speed, the max internet speed, the minimum internet speed? So here we go. Yeah, so 2 Mbps download speed for this first cluster, 0.8 download speed Mbps for that cluster, etc. So you also have the maximum internet speed. Someone tested a total of 45 Mbps here. Okay, and then move on to our third data set, which is nighttime lights. We can generate nighttime lights for that area. So again, we could compute the maximum nighttime lights, the minimum, the maximum, the mean, and here what we call a standard deviation. This is a bit more technical. Basically, what is the variation of that data set? That's what the standard deviation measures. But yeah, these are a bit more common, commonly used. These, the minimum, the maximum, and the mean or the average. All right. Okay, so GDF with features. We could also just take a look at this table. So, okay, we have OSM, we have UCLA, and how does nighttime lights look like? So again, in this circle, you have now nighttime lights. So this was internet speed, and at the end of it, we have 4 new columns. The minimum, I think, it's a measure of the luminosity. So I forgot the specific details, but in general, the higher the number, the brighter that area is at night. So that means there's establishments or there. So now with this table, we could visualize it again here. So, okay, here are our familiar circles, but now there's a lot more information for each. As you can see, like this cluster has 10 points of interest, POIs, 4 restaurants, 1 school. The nearest bank is 2 kilometers away, and etc. So now we're at that point where we've done feature engineering, and we're ready now to. We can still do some more data exploration before we move on to the model. And usually what we could do is, since we've done a lot of work in preparing this data set, which with each circle having statistics, then we could save that for now. So right now, we could save this table as a geo package, this file. Okay, so time check, it is 11:28. Okay, the next exercise will be more about just visualizing this data set more. But does anyone have any questions about what we did and the methodology or the process? Feel free to ask. Okay, there are no questions. We could proceed. So, okay, we have a good data set now, and we could explore this data set further. So here, basically, we're just downloading the same. So let's say you were done with this analysis, and then you saved it somewhere, you went back. So let's say if you save this file somewhere, you could have a checkpoint and work on it again. So that's one way of doing it. Okay, but let's just save this because this is what we worked with. So I just ran this again. So I don't use the one that's currently saved. And you could run this if you want, but since we have this data set with us from the previous exercise, you don't have to run this anymore. And yeah, what we could do is do a bit more visualization. So this section will be more about doing more visualizations using what we call the Folium library. So as you can see, we've had this map where you can zoom in and zoom out. And we haven't really talked that much about it. But basically that Python library that lets you do that is called Folium. And so we can start off by just getting the, EPSG. Okay, let's try using the Cambodian projection. But 3875 also works. So if you put here 3875, ESG, wait. Let me check that again. 875. It's 857. Yeah, so we should change this projection. I think I meant to do 3857 instead of 75 because this projection can be used worldwide. But okay, I think I mixed it up. But yeah, we could use that projection for this because we're just looking at the center of Cambodia anyway. So it's not super strict. We're not changing an entire administrative boundary. So anyway, so when you make a map, you can start off by creating a blank map without anything. And what volume needs is just the center of the map. So we got the latitude and longitude of the centroid of Cambodia. It should be around here. Right? And then what you can do is we could actually customize this map. So right now it's using the default OSM map, but we could use another base map called, use the CartoDB positron base map. So as you can see, this one looks a bit different because it uses a different base map. And you could also use a Google satellite base map here. So instead of looking like this, you could use Google's actual satellite image. And you just have to change a setting here so that it knows to read from that instead of the CartoDB's positron map. So CartoDB is another company that provides tools, also might be services on geospatial web maps. Right, and then what we could do now is download the administrative boundaries of Cambodia level 1. So yesterday we've done this exercise, but yeah, maybe we could go to this website and see geo boundaries. So it's also an open data source of across the world. Let's say Cambodia. See, so if you just search Cambodia there, we have different data sets of the level of that you can download. So level 0 looks like this. It's just the whole country. And as you go deeper, level 1, level 2, level 3, you could see a more detailed version of the map, right? So can we click this? Yes. Nope. So let's see if we can. Oh, cool. So maybe this is one we could look at this. So this is level 1, and admin bounds level 0 rather, and this is level 1, and this is level 2, and then level 3 looks like this, right? So this is what you've been using yesterday, and it depends on your analysis which level you would use. Is it level 3, level 2, level 1, or level 0? Right? And then from here, so we've downloaded level 1, and then here we could actually plot that, the one on that website here in our folio map. So see the admin bounds for Cambodia. So admin bounds is working with admin bounds data is very common in geospatial work. So yeah, so it helps to be familiar with how to work with this data set. Oops. Okay. Next, remember the circles that we developed earlier? We could add that also to our map. So let's just yep. So what we did here is we assigned the admin bound per circle. So remember these are the circle information we had earlier. Now we added the name of the area of the region. And there's just 611 circles, but now we know from where they are. And what we can do is just filter it to what's in the capital. So there are 35 DHS data sets in the capital. So in Phnom Penh, there are, this is how if you were to plot only, this is how it looks like. So the difference now is that there are admin bounds around the circles, and you can clearly see where the DHS clusters were surveyed. So you can see there's a lot here concentrated in this region, and less surveys done on this area. Okay. And maybe you could look at another area. And in this area, you have 26 clusters. And if you were to plot this, it's here. So this was in Phnom Penh. Now you plot what's in here. These are the DHS clusters in this area. And as you can see, you still have the information we derived earlier from OSM, how many schools, how many banks, how many malls, what is the internet speed, and how bright is the nighttime lights at night. Okay, so that is geo-visualization. So using GeoPandas and Folium, you could make all sorts of different plots just to, even if you don't need to build a model, we could actually go far with just data wrangling and visualization. So later on, you could also do things like filters. So we could have a drop down here, and you could say like, hey, I only want to see schools. Or I only want to see, rather that's for POIs. I only want to see DHS clusters within this area. Okay, so is everyone already here? Could I have a raise of hands if you have, if you are where, if you could see the same map on your computer? Okay. So so far so good. I hope today's session is much smoother as well. Okay, so now that you've seen what we could do when we create a folio map, we can go back again to cleaning the data set. So one of the first things is checking if there are duplicates. So this is actually a common problem in any data analysis application. There are duplicates. There could be duplicates in your data set. Sometimes I've had an experience where dealing with a client that has customer data and they have customers with the same ID. So it's hard for me to distinguish which customer actually did this. But for us, since we're working with DHS clusters, we could check if there are duplicates. So we could use this DHS ID. And then you could use this function called duplicated. And it will say for each of the 611, does it have a duplicate or not? But what you could do is, this is what I usually do to check how many duplicates there are. And it says that it's 0, which is a good thing. It means that there's no duplicates on the data. And when we downloaded the data and processed it, each circle is unique. Sometimes when you have duplicate data, it will really interfere and mess up the analysis. And one way of deduplicating it is this function in Pandas. In the Pandas library, drop duplicates. But since we don't have any duplicates, it won't change anything in the data set. Yeah. And you could also do the same, but with the geometry instead of the ID. checking if there are duplicate circles. So they could have the same ID. They could have different IDs rather, but be the exact same circle. So that's also a problem. But seems like there are no. That's not a problem for this as well. Right. So dealing with duplicates is one issue, and another issue is, or rather, one EDA or exploratory data analysis we could do is checking the ranges of values. So this is just really for people to get a sense of how big or how small these values are. So for wealth index, it's as you can see, the maximum value is this number, and the minimum value is this negative number, and this is the average. And for POIs, you can see on average there are 90 POIs in a circle or a DHS cluster of 2 kilometers. On average, there are 20 restaurants. The average speed is, let's see, average upload speed is 1.3 Mbps. And then we can also do plots on the wealth index. So this is what we call a histogram. Usually, what we check to see what kinds of, not only just the maximum and minimum, but see how much of the data is concentrated at which values. So as you can see, there's a lot of data points here. So how to interpret an histogram is this is the wealth index, where the minimum value should be this number, and the maximum value should be this number. So, and then in between, this is how many clusters are in this have these values. For example, you have more than 30 clusters around this value. Yeah, so sometimes one of the problems is, so this one looks okay, but sometimes the data set looks a bit weird. For example, you might have just a really long bar at 0, but in fact, those are the nulls, and there aren't actually 0. So sometimes that happens, but in this case, we were okay. And another thing is handling nulls or missing values. So sometimes you would have a data set where the column has missing values. But in this case, we don't have missing values because we processed it ourselves. But in other cases, if you have missing values, you won't be able to. You would need to do something with them before you run a model. Right. Yeah. So this is the histogram, and one other thing before you build a model, what you could do is make what you call a scatter plot, just to see some kind of relationships between the wealth and the features that we computed. So in here, what I did was to make a for loop. So for every one of these statistics that we calculated, what is the relationship between the wealth and that variable? And yeah, sometimes look a bit weird. So I think this one, the nearest ATM, doesn't really matter. Whether you have a high wealth or a high wealth or low wealth, is just the nearest ATM could be near or far. It doesn't really matter. But sometimes it's a bit more descriptive. So for example, there's some pattern, I think, which one was it? Nighttime lights. Right? So if you look at nighttime lights mean, This one. So there's a bit of pattern here where the higher the nighttime lights, the higher the wealth index. But there are also some areas where it could have a high wealth, but it was just not captured by nighttime lights. So yeah, this is one way of having a sense of what your data set is before you build a model. Yeah, so this is what we call EDA in our workflow. And then I think the last thing I'll talk about before we go into the next half is model design. So model design is about number one is making what we call the final table. Sometimes we call it the analytical base table for the model. So this is what we've been working on actually this whole time. So remember, each row is a DHS cluster, and each DHS cluster is up. We made a 2-kilometer buffer under each cluster, and then we have the wealth index of that cluster. And using the different kinds of processing, we computed a lot of statistics for each cluster. So yeah, does anyone have any questions on this approach? So this slide summarizes all the things we've done in the code so far. Okay, so yeah, there's actually just 3 here, but actually it's a lot. If you could remember, in our code there were this many this many feature columns. We could count them actually.
Hello, sir.
Joshua.
Okay, so they're 26. 26.
ជាថ្មីម្ដងទៀតខ្ញុំបាទធ្វើសុកចន្ទថនខ្ញុំមានសំណួរមួយទាក់ទងទៅនឹងទិន្នន័យនេះនៅពេលដែលយើងបញ្ចូល data រួចហើយវាចេញជាលទ្ធផលថាតើលទ្ធផលដែលយើងចេញនៅក្នុងកម្មវិធីរបស់នៃការវិភាគហ្នឹងអាចយើងអាច convert វាទៅ file Excel បានដែរឬទេ
Yes. I could demonstrate that right now. So let's see. So good thing we were just talking about the analytic base table. However, okay, so there's a couple of things you have to consider with this data set. So remember, we've been working with this table, GDF with features. And one of the things about it is it has this thing called a geometry. So normally, when it comes to data sets with a geometry, we would export it as a geo package, because that geo package format, sometimes a GeoJSON, is what GIS tools can easily read. But we could also actually save it as a CSV. So I'm just looking for the file name. This one. So we save it to a geo package here, but we could also save it to a CSV. The thing is, we just lose when you save it as CSV and load it in a GIS application, it might just not understand how to read the geometry column right away. So we would have to give it additional information. But if you want to open it in Excel, you can just for inspection, and even if you don't want to map it. So I think you could do this. CSV.
What you can
maybe I think it's CSV. Yep. So they should be saved here. and you can download it here. But do remember the DHS data restriction. So yes, we can only use the DHS column rather just for this workshop. Yeah, and here I downloaded it and I'm opening it in Excel. So yeah, so I'm viewing it now in Excel. I have the same 600 rows, and I could use this for any further analysis I want. And actually, we could do that again. So index equals false, and then re-download it because there was an annoying extra column that got saved, and so just do that again. See, so we just remove that first column. But yeah, so this is one way of saving this data set and viewing it in Excel. So does that answer that question? Oh. Okay, thank you. That was a very useful question. I think a lot of other people might also be interested in how they could view it on Excel. So I think I'll just cover these before we go on a lunch break. So so far we've been talking about the DHS data and all that data wrangling, but we haven't actually talked about the model yet. So let's just have a quick overview of types of classical machine learning models. And okay, second. So when it comes to choosing a model, the biggest factor is the nature of the data. Can the data be formatted as a table or is it pictures? So for what we've been talking about so far, we actually didn't have to use satellite imagery for this use case. So our data set is what we call a tabular data set because as you can see, you can save it in Excel and view it in Excel. But in more general terms, when it comes to choosing a model, it depends on the structure of the data set. And really also what you can do is also look into the academic literature on what types of models are handling the use case that you're talking about. But for tabular models, we have a recommendation. We tend to use random forest quite a lot. So these are 3 examples of the machine learning models that you use on tabular data on tables. And there are each of them have different considerations. But we do like random forest, and while I said it's slow here, it also depends on the data set size. So on data sets that don't have more than 100,000 rows, then random forest works pretty fast anyway. And yeah, so you can just look at this slide as a summary. And we could dive deeper into different kinds of models, but for the purpose of this workshop, I think might be better to center it around the geospatial applications. And for now, we recommend random forest. And sometimes you could try out light GBM and logistic regression. It's okay. Maybe you don't have to try it. The first, you could try it, but it's okay if it's not the first thing you try. And we'll talk more about this later, but also before you actually train a model, we also consider the we have what we call a training set, a validation set, and a test set, right? So one of the things about machine learning we've been talking about is that it relies on data to be able to train a model. However, we also need data, not just to train a model, but to also evaluate its accuracy. And we also need data to determine if the refinements on the model are making sense. So we need data for these three things: training, validation, and test. And sometimes we just have two, just training and validation. Like we just have these two as just one thing. But in more, sometimes you'll see it as three. So and the point of this slide is just to tell you that okay, a while ago we've constructed a data set of 611 beaches clusters. But actually, not all 611 will be used to train a model. So we will leave out a section of that model. You will rather leave out some data points so that they will be for model testing. And one of the reasons why this is important is because if you use the same data points for model training and model testing, then your test metrics will be overly optimistic. So you might find your model has, let's say, it's 99% accurate, but that's actually because you use the same data set to test it and to train it, when in fact they should be different. So more on this later, but heads up, they will be doing this split. Yeah, and with that, I think we're just right on time, just before hitting 12, and maybe we could have lunch. And in the afternoon, we could talk more about model development and computer vision. And yeah, we hope to see you back at around 1 p.m. And if there are other questions from this exercise, feel free to approach me or Ren for further questions. And yeah, thank you for this morning. Let's have a good lunch first.
So thank you. So this afternoon, again, so another project in our book for it's a folder. We understand.
We adjusted the program again. So instead of having two hands on activity,
ក្រសួងសេដ្ឋកិច្ចក៏អញ្ចឹងដែរហើយខាងខេត្តថ្នាក់ខេត្តក៏អញ្ចឹងដែរពីព្រោះការដែលយើងឡើងបោកបទបង្ហាញនេះសេចក្តីត្រូវការរបស់យើងសេចក្តីប្រហែលរបស់យើងវាមាននៅក្នុង record អញ្ចឹង
Thank you very much. So yeah, I hope everyone has had a good lunch. I also love the food here in Cambodia. I wish there were more Cambodian restaurants back in the Philippines. But yeah, so now we move on to developing the model itself. So in the morning session, we've talked about what ML is, machine learning, and how we prepare our data sets for a sample machine learning use case. And we used a wealth estimation use case using DHS data, using OSM data, UCLA, and nighttime lights to be able to come up with what we call an analytical base table, which summarizes all of the information that you would need contained in a table so that you will be able to predict a model. So yeah, let's move on to model development. And actually, if you checked your Google Colab, you might have noticed that the runtime was disconnected. This usually happens when you leave Google Colab idle, or if you step away from your computer for, I think, 15 minutes, it will disconnect because it's part of Google's free tier thing. So you can just click reconnect so you could connect back to it. And you could check if the code still works. So remember, we were working with this geodata frame earlier, GDF with features. And if you run it again, you would see you still have it. So the runtime was disconnected, but when you reconnect, you should be able to work with the same table just like earlier. So can I confirm? Could everyone just type this cell and run it? Does your Colab notebook run just the same way as it did before lunch? Could you raise your hand if it works? Okay. Or does people need more time? Okay. So if people are okay, I guess we could proceed. Okay. So first thing, model development and feature engineering. This is something we already did earlier when we built this analytical base table. So it's one of the steps that's just before the model experimentation itself. Remember that this is just a recap. So from each DHS cluster, we created a 2-kilometer circle radius around it. And so that's what we mean by AOI geometry, area of interest geometry, which in this specific case is a 2-kilometer radius circle. And then for each circle, we computed different kinds of metrics. So the easiest one to explain is, for example, OSM. So we have different kinds of points of interest from OpenStreetMap, and we counted the number of points that are within each circle. And then we also computed the average internet speed, average upload, download, and Mbps. And we also computed the average, maximum, minimum, and standard deviation of the night light data. Right. So this is what we did earlier. Feature engineering all of these features, the POIs, and the UCLA. And I guess before we, just additional notes on feature engineering. So one thing is the null. So earlier we didn't have a problem with null because all of our data sets didn't have missing values. But sometimes you would need to fill in the nulls with a certain value. And basically the idea is you fill in the null with the value of your best guess of what it is. So right now we're dealing with geospatial data. So one way of filling in the nulls, if it's spatial data, is to get the weighted average of the neighboring data points. So for example, here you have a missing square. We don't have data for it. But if you take the average of all of its neighbors around here, you get the value of 8. So you do the same thing here, you get 11, and here you can get 12. So that's the basic idea of how you could fill in nulls using the spatial neighbors. So basically, the data points that it's close to. But yeah, right now we didn't have to deal with that problem. Some people just drop some data sets with too many nulls. Sometimes you can do this if there are some rows in a data set that are missing everything. But sometimes if there's only one column missing, it might hurt the model if you drop them, because that's still some information that you're losing out for the model. And sometimes you just assign a separate value for nulls. And if you work with geospatial data, sometimes they do this by default. So sometimes you might see a negative 99.9999 value. It actually means null. But some people might think, oh, I have a data set that it's supposed to measure the elevation in meters from the ground, and then you see values of negative 9999. No, that doesn't mean that that certain area there's a huge hole in it, but rather it's just because there happen to be no data there due to some could be a limitation of data or some kind of processing error. So it depends on the data set, but just expect to have to encounter this sometimes when you're working with geospatial data. And the thing about our approach is, since we're using a random forest model, this is actually pretty okay in filling in a null value with a default value. So if you noticed earlier, we filled in 999999 for the column, which is the distance to the nearest restaurant if there are no restaurants within a certain radius. So that's one way of filling in the nulls. Yeah, sometimes you might also need some transformations. One thing they do is the standardization process. Basically, this is your original data set, and you do this thing called z-scoring to make sure from this distribution, it will look like this distribution. You do this when you're using logistic regression or neural networks. But if you're using random forest, there's no need to do this. But take note, if you're using other models, you will need to do this. Yeah, so for tree-based models, usually it's not necessary. So if you noticed in the Colab notebook, we didn't have to do that. Right, so maybe from here on out, we can try one experiment. So we already have some features, the ones we computed, and we could separate the X and the Y, and then we can train a model and then see the results. So right, let's train our first model using the notebook. So let's go back to the Colab notebook and develop our first model. So remember here, we still have our GDF with features. So, okay, we could run this cell. So let's go back on the Colab notebook. And if there are any issues with Google Colab, or you might feel free to raise it with my colleague Ren, who's will be happy to assist you. Right. So, okay, we have this data set. We've been talking about it all morning. Let's train a model. And what we could do first is train a baseline model. So just to see how fine-tuning the model looks like. So what if we only had POI counts? So we did have a lot of features earlier, around 20 plus, with a little over than 20. But what if we just had one feature, POI count? Right. So one thing, and then one of the other data preparation steps we could do is separate the X and the Y. So usually you would hear this in machine learning. X corresponds to the features or the target, or rather the variables that will predict the Y, so wealth. So what this means is that we are using just the POI count to predict the wealth index. So because the reason we're doing that is because the wealth index is based on a survey which isn't a full census. However, POI count, that's something that is available across the entire country based on OSM. So we're using POI counts to predict wealth index. And then the next thing is separating the train and test set. So you could see how the size of these in a short bit. So remember this X, if you type shape, you will see how big it is. So remember 611, it's the same number as we've been dealing with earlier. It's still the same number of DHS clusters. So it's still the same 611 circles. However, after we split it, if you look at, and it's okay, before that, look at Y and still the same shape. And then if you look at X train, you can see that it's a smaller number compared to 611. It's only 488, but still large. And what about X test? So it is 1, 2, 3. So what we did was a 20% split. So that's usually a standard rule of thumb, an 80-20 split between your test set and your training set. And basically what this means is we will use 488 data points to train the model, and then the remaining 123 to evaluate the performance of that model. So of course, we're not actually using all 611 to train the model. And the way this was split was random. So it's a recommended split. It should be random so that there's no bias in the data. If you look at X-train, how does it look like? It's only one column. It's just POI count because that's what we specified over here. And then if you look at Y-train, it's also just one number because it's just the same as the wealth index. Right. So okay, we can just run this and see how our first model looks like. So I'll first train a random forest regressor. So this is a common library using sklearn. So this is where that function came from, the scikit-learn library. yeah, almost all data scientists use this as a go-to first model when it comes to the regression. And what I mean by regression is predicting the wealth using the POI. So yeah, because there's a different kind of machine learning task called classification, which is different from regression. But right now, just think about wealth versus POI counts. And okay, we could run this, and you will see a plot and some statistics, R squared, and for train and test, right? So what does this mean? So even if you're not developing a machine learning model itself, I think it's important. This section on how to evaluate machine learning models is important, because even if you're not making them yourself, maybe you'll be using someone else's output, or your colleagues' output on their machine learning model, and they will be reporting their findings to you. Hey, we built this model. It is 70% accurate based on the R squared. So if you're confused on what that means, we will explain that here. So yeah, the first thing is, I think what's helpful before we get into the number specifically is the plot. So we have a plot here that's called the predicted versus the actual plot. So this x-axis represents the model prediction. So the random forest model predicted this value, but the true value is this. And we colored it based on the training and test set. And ideally, if this was a perfect model, then we would have every point on this line. So if the point is on this line, it means the prediction is the same as the actual value. Right, and yeah, maybe we could go back to the slides just to explain that further and also explain R squared. In general, the R squared is a value between 0 and 100%. And the higher the value, the better the model. And between these two metrics, the test R squared is better because it is representative of the actual accuracy of the model, because it's being used on a portion of a data set that the model didn't see. This train R squared is good also, but should it be the final estimate for the model performance, because it is naturally over optimistic. So this is, if you can see, train is usually higher than test. And what we report when we say a model is 64% accurate, it should mean the test set. And if someone reports to you a model is 99% accurate, maybe you could ask them, maybe is that from the train set? So maybe they're trying to fool you, or maybe they're just been misled. Right. So that's our first model. So if you can see, a lot of the work was actually in the data preparation, and that's usually common in a lot of data science use cases where a lot of the work is in the data prep, when the model part is actually quite fast. And here I'll explain to you more what we mean by the performance metrics. Yeah, so what we saw here was the R squared. You would see and hear data scientists talk about this a lot. And the textbook answer of what R squared is it's the percentage of the variance explained by the model. So, and the closer the value it is to 100, the better the model it is at predicting. And you could look at these charts to see how that scatter plot changes depending on the level of R squared. So this is an example of a very bad model, the one on the bottom right, where that is very far from the line. And what the story behind this is, it's really a model that just doesn't know any pattern in data. It's just giving random predictions. And you have in the middle these okay and good models at 40 at 80%, where it's closer to the line, and but not exactly. And in the real world, you would see majority of models are somewhere between okay and good, because there really is no perfect model. And there's a quote actually in statistics that all models are wrong, but some are useful. So if there are some stakeholders that expect, oh, why isn't it 100%? So that's not really the point of why we do machine learning. The point is we could make better decisions, and having a good model is just part of that. And on the upper left, you see an example of a great, or maybe almost too perfect model where it's 100%, everything is on the line. And actually, if you see a model with this kind of result, it actually, you should be suspicious, not happy, because it's too good to be true. And usually, this means that there's something wrong in the data processing that made it 100%. All right, and R squared, it's a percentage, so it means it's independent of the original units. So for example, if we're trying to predict the income level in, let's say, USD, it doesn't measure it in USD, but rather it's just a percentage. And the good thing about that is it's an easy and intuitive way of understanding how good the model is. So is it closer to 100 or not? That's how to interpret it. However, there are certain cases where it's better to understand the original units. So, okay, how good is that model? Or if we say, oh, it has an R squared of 70%, but okay, but how good is that in terms of dollars? How good is that in terms of meters? And I think in the first example we shared yesterday, it was in crop yield estimation. We use a different metric called MAE, or mean absolute error. And the thing about this, along with the sister metric RMSE, is that they are both they both quantify the error in terms of the original units. And this is how it's, I guess, a visualization of how it looks like. So again, we have the predicted versus actual plot, and the closer it is to the line, the better the model. And what these metrics measure is the distance between these points to this imaginary line. So the further this point is from the line, the larger the values, and that means it's a bad thing. So what the mean absolute error is basically computing all of these distances first. So how long is this line? How long is this line? How long is this line? The vertical lines, adding them all up. Not rather adding them all up, but rather getting that error, getting the absolute value, because sometimes it's different depending on which side, and getting the I think this is a typo. Should be the mean average. Yeah, so taking the average error. But yeah, basically the short answer is you can use these units if you're working with if you need to interpret your error in terms of the original units. Sometimes you can just report all three of them. MSE, MAE, R squared. Yeah, so in our use case, we use R squared because the units of wealth weren't interpretable to begin with. So DHS gave us a number, but it's not measured in dollars. It's just a general measure of wealth. So it made sense for us to just use R squared and not really. We could report it, but it will be hard to interpret MAE and RMSE. Okay, so and before that, I guess I'd like to have a brief segue into a different set of metrics. So what we were working with all this time is a regression task, but there's also a type of machine learning task called classification. So in this case, we have a different set of metrics called accuracy, precision, recall. And one use example this that I mentioned earlier was the example of spam classification. So is this email spam or not? So it's a yes or no. It's classifying it rather than predicting a value, a continuous value rather. So one way of measuring it is among all the emails that were spam, how many did predict to be spam? So that's accuracy. And for precision recall, there's all these explanations for them. Yeah, and then so you could just read this, but basically, just like what I said before, if you have an R-squared value of 100%, we might be suspicious because it's too good to be true. And it's the same for classification metrics. So if you have your precision, recall, accuracy, even the F1 score all 100%, then there might be a problem. And what data scientists call this is the overfitting problem, where the model is just basically memorizing the training set without learning patterns. Yeah. So okay, going back to our model, it's just we can be better. Because at the end of the day, we just used one feature, just POI count. What if we added everything else? So what if we use all of these features and train the model? So we do the same thing, separate X and Y, generate train and test, and then we do the same thing, train the model. And then you can see it's so much better compared to the earlier one. So compared to this one, where the points are further from the line, we have now the points closer to this line. So this is what we're looking for, but at the same time, it's also not too perfect. There's still some variation across the data points. And yeah, and then you can see it also here, the difference between the train and test. So of course, on the training set, it will be higher compared to the test set. But compared to the earlier ones, there was still a improved effect. Oh wait, so I'll just go here. So it's 75% here, but earlier it was just 64% here. So this is part of model, how we improve the model. One of the most common ways to improve a model is to really add features so that we could have a better prediction. And we make sure that we're just not adding any kind of feature, but we're adding features that are indicative of wealth. So for example, in our use case, the other data points were the internet speed, which is an indicator of wealth, and nighttime lights, which is also an indicator of wealth. So even without doing machine learning, I think it's reasonable to say that better internet speed and brighter lights mean there's more wealth, and that's why we chose them as the features for our model. Right. So congratulations, you have a machine learning model here with 75% R-squared. And of course, there's still more ways of making it better. So you could do these things. You could try more features. You could also tune the models, what we call hyperparameters, and try other model types. But for now, we tried this one, and usually this is the technique that gives you the best results. This could also improve your results, but not as much as this. So make sure to try this one first before doing these other two. Right. So yeah, and so this is what we did. We changed a few things, and the model improved its accuracy, or rather R-squared. And yeah, one thing you can also do is use different kinds of models. So logistic regression, random forest, like GBM, and you could record if you have time, you could record the different settings using these different models and estimate the R squared for all of them. So usually that's what data scientists do if they want to really find a high accuracy model. Right. So now we've trained a model here. Next is, but sometimes it's not enough just to have an accurate model. A lot of times people want to understand why that model is accurate, and among all the features, which are the features that are contributing most to the model. So for random forest, there's this thing called a feature importance, which can quantify which of the input features actually contributes high. So here we see that it's actually these two things, the number of devices and the nighttime lights that contribute most to the model. So for devices, this is actually the number of I think from UCLA, the number of devices that click on the speed test of UCLA in that area. So that means there's a lot of people who are connected to the internet in that area. Even if they don't have a high internet speed, the very fact that there are people there who have a device means that it's an indicator of wealth. And also the nighttime lights is a big factor. That means if there's a high, it's brighter in that area at night, then it's important. And there's also this thing called Shapely explanations, which I won't dive deeper because Ren talked about this yesterday. Basically, it's a way to interpret your features, just like feature importance, but there's a bit more detail into it using this B-swarm plot. All right, I think that was a lot. I think I'll pause right now to take any questions. Will there be any questions on the features or on interpreting the model? I'll take questions now if people have questions. No? Okay, if there are no questions at this point, we can actually proceed now into the last section. So, okay, we've trained the model, congratulations, but how do we actually use it? So remember, going back to the problem definition, this is about wealth estimation across the entire country. Right. And this is a recap so far of what we did. And if you could remember, summarize again. So remember, these are our DHS cluster radius. So there are 611 circles here. And using this data, we trained a random forest model. Okay. But now that we have a model, what do we do? How is it going to be useful in the real world? And what we do is we do what's called model rollout. And because of this random forest model that we trained, we can make a map like this. So in model rollout, the first thing we do is we generate grid tiles, these squares across the entire country that are just blank at first, but then we can give color to them by assigning a value based on the model's estimate of wealth on that area. So as you can see, in this map is the rolled out model across the entire country. So you have here Phnom Penh, the capital, which is the highest wealth. That's the scale here. So the closer you are to blue, the higher your wealth. The closer you are to red, the lower the wealth. And then you'd see the highest wealth is here. and then it becomes a bit more yellow just outside, and then before it's orange, and then it's red. And then you can see also here a bit of tinge of blue with CM rep. This blue and then yellow, orange, it becomes red. So this is a good one way to really quantify your wealth across the entire country using your open source data. And remember that before we only had to survey these many areas, but using this data set, we were able to extrapolate and give a prediction to every other area within Cambodia. So, but of course, that there's some no model is 100% perfect, and if there were more data points here, the better the model will be at estimating this. But this is a start, and especially for projects when it comes to poverty alleviation rather, then this is a good way of making sure we have poverty estimates even without having to run a full census every year. So, and with the UNDP, our project with UNDP, this is what we're doing across Southeast Asia. All right, so how do we do this? So now that we have a trade model, how do we do model rollout? So I think we have the Cambodian, you don't have to download this. We already have the Cambodian admin boundary. So first we have to just, the first step when you do model rollout is to download again and process the data sets, not just for the DHS clusters, but also for everywhere else in Cambodia. So that's really the first step. And another step, so here is the Cambodian admin boundary. And then an important step is generating these grid tiles. So these are squares all around Cambodia. And we have this function that generates them for you. So there are a total of 8,333 tiles at a certain resolution level. And it looks like this. So I forgot how this translates into meters, but there's a certain, depending on the zoom level, the higher the zoom level, the smaller the size of the grids. So this is a grid across Cambodia, and right now there's no information here, but what we plan to do is to add the wealth estimate to each and every square here. So again, we'll be working with the OSM, the UCLA, and the nighttime lights. Okay, so let's read that again. We already downloaded the OSM file from earlier, but now we will compute features for each of those squares. So using this, you can take a look at this. So you have, for each square, you have the same thing. Remember the number of POIs, the number of restaurants, the number of banks, the distance of the nearest supermarket, etc. So instead of the 611 circles, you're doing it now on the 8,300 tiles. So, but it's really the same thing. Instead of circles, it's now tiles. And then we do the same for UCLA. So we don't have to download UCLA since we've already downloaded it. So what we just have to do is load it to our existing data set. Okay, so processing Ookla takes a while. It will take around 5 minutes. So maybe you could take this time to have more questions on the approach. Yeah, so this is just run for 5 minutes. I could also go around if there are specific technical questions. Hmm. Hmm. Right. Right. Yep. Thank you for someone pointed out that the default CRS was 3123. And yeah, and good catch. We did forget to change that. So this was actually the Philippine projection. We just it was an oversight on our end, so it's our mistake. But yeah, we could rerun this analysis with a different metric using the Cambodian projection. So my apologies. And yep, to the gentleman who pointed that out, yes, you are correct. And thank you. When we send this notebook out, we would be providing you with the correct projection. And who knows, you might even have a better performing model than what we made. So yeah, if you use a different projection, yeah, the way you compute distances and the shapes might just distort a little. Yeah, I think what would be affected just mostly the distances. I do remember there's these restaurant the nearest, so this might not be a totally accurate count, but I think this should be the same. Because the intersection operation shouldn't be affected by no matter what projection you use. But still, it's still best to use the correct projection. So yeah, actually that's good. Yeah, so maybe I think this is what's going to change. But everything that just relies on intersections, like everything else, might not have to change. So yeah, thank you. Let's see if it's done. Right now, we'll just continue. We're almost at the end. And that's one of the good things, I guess, also when you have when you use Python, the Python workflow is because everything is transparent. All of the steps are transparent, and if you use a notebook, everything is transparent. So when times like this, someone can review and say, "Hey, maybe you had a mistake here," and "Oh yeah, there's a mistake here." So it's one of the benefits of having using a library like Python, because everything is explicit. Everything is written out. Okay, so are we done with the UCLA? Yep. So we're done with this. And I just leave this like this for now for consistency. But okay, so we make features, and then so it's the same thing. We make UCLA features. We made nighttime light features. What's this? Yep. Right. So I will show you the fruits of our labor in the next cell. I think all nighttime lights also takes a while to run. But yeah, this is the result. So for each square, you have the number of POIs, the distance of the nearest school, and everything. It's the same set of data, same set of columns as the HS circles, but now it's just squares. And then okay, the last step, the step we've been all waiting for. How do we predict? So it's actually just one line. So we do have a model already. So if you type model and you run it, you have the random forest regressor that we've trained earlier. And what happens is you use that model and you predict it using all of the features that we computed from OSM, from UCLA, and from nighttime lights. So we have here the predicted wealth index. And if we look at the table, we have added a new column to that same table. So here we have predicted wealth index, which is this number. It could be negative, could be positive, but the higher the number, the greater the wealth. And with this, we could make a folium map again. And this should conclude this session, this section on classical machine learning. So here we are at the end with this map showing the wealth estimates across the entirety of Cambodia, and you can zoom into this Siem Reap region. There's one blue here, and it's quite near the airport. But yeah, congratulations, you have trained a machine learning model end to end. This workflow that we talked about earlier, we actually went through all of the steps. So this one, we went from problem definition to data wrangling to EDA to feature engineering, experimentation, model evaluation, and even model rollout, which is not part of this because it's usually done after you build a model. So coming back to this slide, you've ended up with this. Right. But yeah, and machine learning we talked about is one task, regression, but there's actually different types of machine learning. It could also be classification, but more importantly for today, it could also be about deep learning and computer vision. And that will be the next section that we'll have, computer vision and its use cases. But yeah, before anything else, I'd like to open again another one round of questions for this. And yeah, for some of you, maybe you could make this even better today by rerunning everything, but with a corrected CRS. Yes. Yes. Yeah, Sam, there's some questions.
មានសំណួរមួយពាក់ព័ន្ធទៅនឹងmodel នេះចង់សួរថាគម្រោង model ដែលយើងកំណត់កម្រិតជីវភាពរបស់ប្រជាជននៅក្នុងប្រទេសកម្ពុជាដោយសម្គាល់ទៅលើពណ៌មួយៗនៅក្នុងផែនទីនេះអាចប្រើប្រាស់ជាផ្លូវការឬនៅដូចនៅខេត្តសៀមរាបគឺសម្គាល់ឃើញមានតំបន់មួយកម្រិតជីវភាពដាក់ពណ៌ Q
Depends on what you mean by official data, but I would say this is different from official government statistics, because I think if you're talking about official government statistics, that requires actual results from actual survey results. However, this could be used also. Not sure if it's official as in you could release it officially, but with the disclaimer that this comes from a model and not coming from household actual survey results, then it will be fine. And actually, in our working on this model for Southeast Asia is actually part of our project also, and we do plan to also publish our wealth estimation models for Southeast Asia. But for your use case, if you find this useful, I think in your own work, we could just file a request for DHS so that you could first get that DHS data, but then rerun everything, and the results, you could use it in your own work. But yeah, did I answer your question correctly?
So just to add to that, whenever we do make machine learning models, a good basis of how accurate or useful it is for, let's say you want to use this output for a project that you're currently working on, what we can do is go back to the model evaluation statistics. And that sort of tells us how accurate or how useful this data set will be. So another thing that we can do is, so we already have this data set. You can go do an inspection for parts of the data set. So it's good that you pointed out that Siem Reap here has a blue dot. And if we can use that as an example, so you can actually use your local knowledge and domain expertise of why do you think there's a blue dot there? Does it make sense that this area is richer compared to the neighboring parts? So so to answer your question, it's actually useful, but we just like to note that this particular output here is just for demonstration purposes. So as you can see, we do get quite a high accuracy, but if you want to use the output, please also use it combined with your local understanding of each area, some government statistics that can support this data set. So essentially, that's a good way to use this output. So it's really combining and complementing the data that you already have. Any other questions?
Actually, I have a question. Like, I was wondering what this area is. It's quite near the coastal area.
Yeah.
It's quite a bit or greenish. Is this like a port? A port city. Does it make sense? This is a bit greener, closer to blue. I'm not from Cambodia, so I'm not sure.
So yeah, since now we have this map for wealth estimates over the country of Cambodia, we actually want to get your input. What do you think about the results that we generated here? So for the next few minutes, it's actually would like you to explore this map, maybe find some interesting parts of the map that catch your interest, maybe because it's correct. Yes, this area is wealthier compared to its surroundings, or it could also be an anomaly of why is this showing up as a rich area when your local understanding of it is it's supposed to be lower or similar to its neighboring parts. So
so
really,
maybe you could just spend around 2 minutes for people to go over this map and look at places they want to look at. And then there's some people who want to share. Maybe this model is very wrong in one area. Hey, it's blue, but it shouldn't be blue. It's red, but it should be blue. Then do let us know because you are the locals and you have better context on how it really works in your country.
So yeah, the example that Joshua pointed out earlier is actually quite an interesting point for us, since it does appear to have a higher wealth index compared to its neighboring tiles, and we also want to understand what's going on in that particular part and why is this appearing wealthier compared to its neighboring tiles. So maybe we can spend 5 to 10 minutes as a discussion. And we would like to hear the thoughts of some volunteers. So please expect people to share, and there will be prizes again.
there any are there any volunteers? We have two goodies to any to anyone who would like to share some of their thoughts on the results, and if they make sense, yeah, we have a prize for you. So, does anyone like to volunteer? Or you might need a bit more time.
Any volunteers?
Okay.
Yeah. Yay, we have one.
បាទតកតងទៅនឹងការកំណត់សម្គាល់ទៅលើតំបន់ឆ្នេរដែលខាងយើងដាក់ model នេះគឺតាមគំនិតខ្ញុំគិតថាចំពោះពណ៌នីមួយៗនៅក្នុងកំណត់សម្គាល់នេះគឺវាមានអត្ថន័យផ្សេងៗគ្នាក៏ថាខ្ញុំក៏មិនដឹងថាពណ៌បៃតងហ្នឹងគឺមានអត្ថន័យយ៉ាងម៉េចដែរដែលបានគាត់ដាក់នៅក្នុងតំបន់ឆ្នេរនេះប៉ុន្តែខ្ញុំយល់ថាមូលហេតុដែលគាត់កំណត់សម្គាល់ពណ៌នេះនៅក្នុងតំបន់ឆ្នេរទីមួយដោយសារគិតថាតំបន់ឆ្នេរគឺមានសក្តានុពលទៅលើផ្នែកសេដ្ឋកិច្ចហើយក្នុងនោះមូលហេតុដែលគិតថាផ្នែកសេដ្ឋកិច្ចនៅក្នុងតំបន់ឆ្នេរគឺភាគច្រើនគឺវាមានការនាំចេញនាំចូលហើយក៏ដូចជាតំបន់មួយស្ថិតនៅជាកន្លែងទេសចរផងដែរបាទ
Oh, so this is actually also a tourist destination. Am I right?
Yeah.
Okay. So yeah, it makes sense since it is on the coast. It's naturally going to be a import-export area. But yeah, thank you for that insight. You get a free prize from the Philippines. It's an ensaymada.
Thank you. Do we have another volunteer? Maybe anyone wants to share?
Oh, another one.
Yay.
Hello. សម្រាប់ជាយោបល់ខ្ញុំដោយសារតែយើងដាក់ផែនទីជាពណ៌បៃតងស្រាលនេះតាមដែលគាត់បញ្យល់គឺគេកំណត់មុំដែលថាតំបន់ដែលមានការប្រើប្រាស់អគ្គិសនីច្រើនជាតំបន់ដែលមានជីវភាពធូរធារហើយតំបន់ត្រង់ហ្នឹងវាជាតំបន់ទេសចរនៃវិជាណាចក្រកម្ពុជាយើងអញ្ចឹងសកម្មភាពទេសចរក៏ច្រើនការប្រើប្រាស់អំពូលភ្លើងអគ្គិសនីក៏ច្រើនធ្វើឲ្យសត្វតឡាយចាប់ទៅមកគេវាជាពណ៌បៃតងអញ្ចឹងតែម្ដងបាទអរគុណ
Yes, it's green because it is lots more light because as you can remember, one of the factors, or rather one of the features of wealth is also the nighttime light. So yeah, it is a good proxy for the wealth estimate, just the night and how touristy that area is. Thank you all for participating in this exercise, and yeah, we do hope that this can inspire you to make your own models for your specific use case, and I hope you see the value in doing geospatial analysis. So again, it can actually save you money because you could extrapolate. It could predict the wealth, or not just wealth, but could be another kind of metric across the entirety of Cambodia. So with that, what we're left with is just the last section on computer vision and the wrap up. But yeah, that closes this section on classical machine learning. And when I say classical, it's data that uses tables. So with that, I think we have a snacks ready outside. So maybe we could have a break for 15 minutes. And then after that, we'll have one last push for the last section. But yeah, we could see you back in 2:35. Okay, sorry. Yeah, we can have just have a longer break.
So we still have a few minutes before snack is served outside at 2:30. You can use this time to rest or take a break first. But if you have any questions or you want to troubleshoot any of the errors you encountered in the notebook, please feel free to approach us and we'd be more than happy to help. Thank you.
Yeah, so yeah, good afternoon, everyone. Glad to have you all here back in the hall after our snack. Okay. Okay, so yeah, good afternoon, everyone. Glad to have you all of here. And yeah, we could proceed with our last section. And if you have any need any help to troubleshoot your Cola notebook from the previous session, then feel free to ask my colleague Glenn for some assistance. So, okay, the data we've been working on so far was based on DHS data, OSM, UCLA, and Nightlight, but we haven't actually used satellite images yet. So, and what are also the use cases for computer vision? So, just an intro to computer vision. So, computer vision is a subfield of machine learning, and the goal of computer vision is to mimic human vision to be able to recognize patterns in an image. So, if you look at this example here, this is a specific kind of computer vision task that detects the type of house. So we did this for one of our projects before for a particular client, and they were interested in classifying the type of house and also counting and detecting those types of houses because it is important for their planning. And I think this was also in Southeast Asia. They are interested in classifying the type of house according to these types. So semi-detached, detached, or a terrace house. And yes, so as you can see, these squares drawn over the images represent the machine learning model's predictions on that house. So if it's yellow, it predicts that this is a detached house. If it's this shade of blue, then it is a semi-detached house, etc. So in a nutshell, computer vision models can classify objects in an image, and the way they can do that is again using human labeled examples, and this is one example. And we'd also like to share one of our previous use cases, what we've done in thinking machines a few years ago. This is now from a project in Colombia. And so one of the problems with, I think it was like a couple of years ago, was the Venezuelan migration crisis. So there were many refugees migrating from Venezuela to Colombia, and we worked with a humanitarian agency called IMAP Colombia, and basically they needed help in detecting where these refugees were settling in Colombia, because there were a lot of them, and they needed to detect where they were, so that they would be able to provide the appropriate humanitarian aid. And the way that computer vision helped here is to detect the change over time. So you have a satellite image from a certain point of time, let's say 5 months ago, and you have a satellite image of this month. And if you would compare the images, for example, in here, it was first a forested area, but then there were settlements and buildings that grew in that area. So that means that is potentially an area with refugees. So based on this model, we were able to detect more than 350 new informal settlements in 68 municipalities in just 1 month. And I think the project team who handled this also worked with a group on the ground who did some manual verification, and they verified and confirmed that these were indeed some informal settlements from refugees that they could assist. So this is another example of how computer vision can help in using a humanitarian use case. And this is another project that uses computer vision, and this is one of our current projects right now, based on a grant, and we're working with a global nonprofit called Conservation International to detect the best areas for restoring mangroves across Southeast Asia, specifically the Philippines and Indonesia, because we have a lot of coastal areas. So the summary of where computer vision plays in this project was to identify that type of fish pond, whether it's this kind of fish pond or this kind of fish pond. So this kind of fish pond is what we would call a natural or extensive type of fish pond, where there aren't many machines to help feed the fish, whereas this is a kind of fish pond which, based on these swirls, they are more mechanized and have a bit more investment. So the way this is relevant for our project is that for Conservation International, they want to target some fish ponds so that they would work with the fish farmers, and then rehabilitate part of their fish pond for mangrove restoration. But the thing is, if your fish pond is of this type, then it's more likely that the farmer will not want that rehabilitation, because they've already put up a lot of capital investment with their fish pond. Compared to here, there's not much capital investment, so there's a bigger chance that they are more willing to participate in that program. And the benefit of that is because expanding fish ponds is one of the reasons why mangroves are being cut down. And so for the past few decades, there have been more and more fish ponds in Indonesia and the Philippines and other countries, which is good for like the livelihood of the local community as well as food. However, another side effect of that is they've had to cut down mangroves, and that also comes with losing their protection against storm surges and also other environmental benefits. So with this program, we hope to be able to plant with some mangroves, and the farmers will get the best of both worlds in such a way that we only consume a bit of their fish ponds, so that we would reforest mangroves, but at the same time their yield is higher because the way these mangroves help make the ecosystem healthier. So basically, in a nutshell, going back to computer vision, that's one of the use cases, and it's, as you can see, it's only one part of a larger project. Of course, there are more things at play when it comes to the applications, but if you can find the appropriate use case where computer vision is helpful, then it's good for you. But sometimes it's not always the first thing that could be the most useful. There could be other things. Right, and this is another project that we worked on. This one is in the Philippines, working with the Jerry Rojas Foundation. And this is basically helping detect deforestation across the Philippines, and not just the deforestation, but also the type of deforestation, if it's due to mining, due to slash and burn, due to product extraction. So we used satellite imagery from 5 years, from 2016 to 2021. And we tried to compute which are the areas that are suffering from deforestation, to be able to help the foundation save and restore more trees. All right, so those are 3 examples of use cases. And now I'll go over and talk about, before I move on, does anyone have any questions from those use cases? Okay, if there are no questions, I could move on and explain the different types of computer vision tasks. So we were just talking about computer vision with a bird's eye view, but if we were to specify the types of computer vision, it's actually 4 of them that we could talk about today. So first is image classification, then object detection, then semantic segmentation, and instant segmentation. So these 4 computer vision tasks are quite, there's a difference to those 4. And in this picture is kind of like a big summary of the differences between the 4. So first off, we have, I guess, computer image classification, where this is actually the simplest computer vision task, because the goal of this is just to classify what is in the image. So it doesn't help you determine where exactly that image, that object is. But for example, you have an image here, it just says, okay, this is cat, this is dog. So the input is an image, and the output is the prediction of what it is, of how it's classified, along with the probability score of how confident it is of that prediction. So if it's here, if you give it a picture of this, a good model will give you I'm 97% sure that this is a cat, and I'm perhaps 98% sure this is a dog. So this is one very common example of computer vision. And in the use case or example of satellite imagery, one example of how image classification is used is particularly this thing called land use and land cover classification. And I think especially the Ministry of Agriculture could find this useful. Basically what happens is you have this area of satellite imagery, and we crop out a certain portion of it, which is this tile, and then we give it to a machine learning model. This is on the represent a picture from a machine learning model, and then it will predict what it is. So this is from an industrial area, and then it will predict this on this industrial. So these are other examples of what other classes there could be. So could be residential, could be crop, annual crop, permanent crop, pasture, dense residential, etc. So then the types of classes that you would have, by classes I mean these, A, B, C, D. The type of classes would depend on your use case and also the model. But yeah, just to have a sense of what's possible, it's when it comes to image classification and geospatial data, it's this land use land cover classification. And later we'll provide an example of that, how that works exactly. Next, we have object detection. So the difference between object detection and image classification is that whereas in image classification, you just give one word or a few words, an image. In detection, it will actually tell you where in that image is that object. So it will give you a box, what we usually call a bounding box per object. So this is usually useful when it comes to when there's many objects that you want to detect. So for example, here, this is a use case on the road where you detect when you're detecting how many cars are there on the road. So your input would still be the same. It's an image, just like the previous one. But the difference is instead of just saying one thing, it will predict all of the locations of everything in an image. But the thing with object detection is that it's limited to just the box. So for example, here, this box is car, but as you can see, there might be like a small space here that's not actually the car, but just the road. But for some use cases, that may be enough, just having the box, maybe more than enough. So yeah, you can detect the bicycle. There's a traffic light here. There's a truck. There's a car. Yeah, and another, if you were to step that up even further, so remember here in object detection, we were detecting the box that encloses or captures the object. Here with semantic segmentation, you would have, it's actually even more detailed because you are giving a classification to every pixel in the image. So the input is the same, it's an image, but the output is what we call a prediction mask. So for example, here, it's a prediction mask where the orange one, I think, is car, blue one could be building, the green is road, this violet one is a person. So difference between here just gives you the box, but here it will give you each pixel of that classification. So this one is also a harder kind of model to train because of it's more complex. Its predictions are more detailed. So that's the general rule. If you want a prediction that's more detailed, usually it's also harder because you would also need a data set that has this level of detail. And lastly, you have, so this is another example of semantic segmentation now in the geospatial use case. So remember we had land cover classification earlier where we, given a crop image of a tile, we predicted the class, but we could take it a step further and then we could have a pixel-wise land cover classification where when you give it any type of image tile, it will predict the type of land, not just of that image as a whole, but each individual pixels. So that could be useful in some cases where there could be multiple land classes in the same image. For example, like 20% is highway, but most of it is really the residential. So for example, there could be houses near a highway. So it will be able to distinguish both. Whereas in the first model, it will only give you one prediction, probably residential because it's a bigger part of the image. And yeah, a common use case for semantic segmentation is actually crop classification and crop field delineation. So especially for the Ministry of Agriculture, this is one of the most common use case of semantic segmentation, where you could given an image of plot of land, you would be able to detect which pixels here correspond to the agricultural crops. And then there's also something called instance segmentation. Because the problem with semantic segmentation is that it actually can't distinguish between individual instances that are close together. So this is the best, one of the best pictures as an example for this. So let's say you have this group of friends, and you want to detect like how many people are there in this picture. So with semantic segmentation, it will just give you per pixel, just detect, okay, this is background, this is black, and then this maybe dark violet, pink color is a person, but it can distinguish individual people from each other. So it's just one blob that is person. However, if with the instance segmentation, it can distinguish between instances of people. So it can say, oh, okay, this is person, but this person is different from person 2, and this is different from person 3, person 4, person 5. And for crop mapping, this could be important. For example, if you have multiple, like say rice fields, or could be another crop, and if you're interested in counting the delineating between certain fields of crops, we want, okay, this part is A, B, C, D. Instead of just having one blob, then you might also want to consider instance segmentation. Yeah, so apart from crop mapping, another application for this is building footprint segmentation. So this is another use case that we've been working on. And yeah, so the thing with buildings is sometimes they could be appear very closely to each other. So just like this image, and if you use semantic segmentation, you might mistakenly believe that, okay, there's just one stretch of buildings here. The model might think that, but without distinguishing, okay, this is actually a separate building from this. And sometimes that matters, sometimes that doesn't matter. So in the cases where it matters, for example, you have a company or organization that wants to count, not just detect the houses in that area, but also wants to count how many houses, because you want some kind of estimate about the urban density, then using instance segmentation might be better for them. So going back to that example earlier, we could talk about the differences about from these four rather. So here, classification, it will just tell you, okay, there's a balloon. It just tell you balloon. But object detection, okay, there are multiple balloons, and here's a box for each of these balloons. But semantic segmentation will tell you, no, here's a pixel, here's every pixel with balloon in it. And then instance segmentation will tell you, okay, it's not just every pixel which is balloon, but this balloon is different from this balloon and from this balloon. So those are the four, I'd say, most common computer vision use cases. Yeah, so from here, does anyone have any questions? Okay, no questions. Okay, we can move on to maybe this is the last segment. So I have a section on neural networks, but I want to highlight something else that we prepared for today. And really diving deeper into land use land cover classification. So I'll walk through the slides first and see, and we can go through the collab notebook later. So, okay, so you've seen earlier this use case of land use land cover land use classification. And the objective of this is to classify a tile of land based on the satellite imagery. So you can say, okay, this is industrial, this is crop, industrial, residential, industrial, etc. And this is using satellite imagery out there that some of them is open source and free. And you can also do this not just at a certain time, but across multiple snapshots in time. So if there's change in the land cover, that's also could be important. For example, from crop, it became industrial. So that means someone built on that piece of land. And one thing I'd like to highlight is this actually a data set of land use and cover. Although the thing is, it's just I think available mostly in Europe. But this is an example of what land use and cover can be. So this is the Eurosat data set of grid tiles across Europe with a corresponding LULC classification. And in this data set, there are 10 classes. So annual crop, forest, highway, industrial, I think herbaceous vegetation, pasture, permanent crop, residential, river, salt lake. So, and this is how many images are there of each type. So there's around 3,000 for images for a lot of them, but some of them are around 2,000 to 2,500. Okay, so these are the types of classifications. And since this is from Europe, let's have one example in Germany. So this sample use case, what if you want to classify land in a given study area? And note that this area might not already been covered here. So this is the images here might not, definitely there's not enough images here to cover the entirety of Europe. So what if there's a new area here and you don't know what the land classification is, but you'd like to know what it is? So let's look at this region, this Kries-Borken region in Germany. And just like similar to what we did earlier in the poverty mapping example where we made squares out of Phnom Penh, of the entire Cambodia rather, we can also make squares out of this entire region and then get the satellite image of each tile. So this is how it's like. But when you zoom in, it looks like this. So this is an example of one tile of that image zoomed in. And then assuming we have a trained computer vision model, we could roll this out across the entire region. So let's say here, I can show you a more interactive example here, but in this region, you classified it according to these 10 classes. And you can see that, okay, there's residential here that's red. There's industrial here that's quite near the residential. And you can see where the crops and the vegetation are across the region. And yeah, so you could filter it. So if you're interested in filtering, you can just filter it. Okay, I just want to see industrial and residential. It's here. And I could also see that they tend to cluster together. They tend to be together. Yeah, so, right. So right now, I think we could spend some time on this too. So maybe we could go to bit.ly APBLULC2. So this assumes that you've already trained a model. I'll be jumping into the second notebook now so that we have time to appreciate the results because training the model also takes some time. So yeah, Okay, so we're here, and I advise you could make a copy again. But yeah, I'll flash this first. So ADB LULC2. Oops, sorry. So I'll give you a few seconds to input this ADB-LULC2. Okay, so here we are, and okay, I won't, in this example, some parts might, there's Google Earth Engine authentication here. So I think in the interest of time, I won't be running through each cell, but instead I'll be talking over the main outputs in this notebook. So it will be similar to what I presented in the slides earlier, but I guess a bit more detail. So, okay, so we have this area in Germany that we wanted to get. So Kreis, Borken. Okay, and then what we want is let's first get the satellite imagery for this region. So we get Sentinel-2 satellite images, and you might hear us talk about Sentinel-2 quite a lot, and that's because it's quite a popular data set to get satellite images from, because number one, it's free, and it is of a higher resolution